All right, so good morning, everyone. Let me first start off by saying thank you so much for coming to NFM. We really hope that you've enjoyed the symposium so far as we head into our third and final day. I'm so excited. I have the pleasure and the honor of presenting our last set of keynote speakers, Dr. Paul Miner and Dr. Natasha Niobe, both of whom are senior researchers at NASA Langley Research Center. Just to give you a little background on Paul and Natasha, Paul earned his master's degree in computer science right here at William and Mary, and he got his PhD in computer science from Indiana University. His research is in design and verification methods for digital avionics, and he's developed methods for formally verifying digital hardware and software for mission and safety critical systems and architectures and algorithms for fault tolerant systems. He's currently a project scientist on NASA's system-wide safety project. And he did not put this in his bio, maybe because he doesn't want us to know, maybe because he doesn't want to think about it. But according to his LinkedIn profile, he's been at NASA for nearly 40 years, which is amazing. So an absolute font of knowledge about formal methods and NASA's role. In addition to Paul, we also have Natasha. Natasha earned her PhD in aeronautical and astronautical engineering from MIT. And her research interests include verification and validation of software-intensive safety-critical infrastructure systems, and certification issues concerning airworthiness of non-conventionally piloted vehicles. In addition to being a researcher at NASA Langley, she's been a staff scientist in the Office of the Chief Scientist at NASA headquarters, and she's currently a senior technologist for Assured Intelligent Flight Systems. She's a fellow of the AIAA, a recipient of the AIAA Robert Mitchell and PEC Doug P. Enzer Young Engineer Awards, and she was awarded NASA's 2021 Outstanding Leadership Medal. Natasha has also been with NASA for quite some time, approximately 6 years as a contractor at NIA, and then I think about 10 years as a civil servant. So I'm very excited to hear what Paul and Natasha have to say today about the evolution of formal methods and NASA's role in that. Anytime I delve into a new discipline and learn about its history, I always find it very interesting to hear about all of the different twists and turns and unexpected challenges and surprises. And I think for the formal methods community in particular, I once heard it said that the community is like little groups of nomads wandering the mountainside, sort of converging at times and diverging at others. And so I'm interested to hear where NASA fits into that landscape since I'm still relatively new there. So thank you very much for being here today. Can we please get a round of applause for our speakers?
All right, well, first, I'd like to thank the organizers for this opportunity to speak. We appreciate it. It is kind of fun to come back to old stomping ground. They've changed quite a bit since I was last here. So anyway, I'm going to be speaking mostly about formal methods TAP because I've not used formal methods in Angular for 10 to 15 years now. So I can only talk about things pretty much up to 2010 timeframe. That's about the last time I got my hands ready. So I'm going to talk a little bit about some of the prehistory. What was the situation here at NASA Langley before the formal methods got started? What was the context? Talk about some of the triggering events that helped us get started, and some of the early work that we did leading to the present. So in the prehistory things, when I started here in 1986, that computer, the SIF computer, was in the lab. It was not really operational anymore. It was, but there were the two computers, SIF and FTNT, were both part of the lab as well as some other fault-tolerant architecture. We had come, the branch was a group that was focused on safety critical systems, fault-tolerant systems design. And from the mid 70s to the early 80s, there was two big competing contracts to do proof of concept of fault-tolerant systems to meet a target reliability, a probability of failure per hour of less than 10 to the minus 9. So this was a pretty serious constraint, particularly given the nature of technology at the time. So the SIF computer was designed at SRI, and the hardware was produced by Bendix, which then became Allied Technology and bought Honeywell, kept the Honeywell name. But there's some heritage there. The FCMP computer was developed by Carl Schultz Waker Lab, which is also a hotbed of fault tolerance at the time. And the implementation of that was done by Collins. So. Now, the processors at this time were kind of interesting. So each of those boxes in there is a single processor with probably roughly 5,000 two-input logic gates. So these were bit slice processors of complexity probably comparable to the original, say, 8088 from Intel. Not a whole lot of complexity. And when I first started, my job at NASA was working on a simulator to simulate microprocessor designs and try and assess how faults might propagate within the design as code was executed. And so I got reasonably good at dealing with sort of 5,000 gate level designs. Complexity and Moore's law quickly outstripped that. And it turned out that the purpose of that simulator wasn't adequately justified anyway. So I was very grateful to have the opportunity to shift into formal methods. So some interesting things about the SIP development is designed at SOI. You've had a number of interesting people at SOI at the time. So Leslie Lamport was there. He was part of the SIP project. Boyer and Moore were there. They did some stuff peripherally with the SIP project. Does everyone here know who Boyer and Moore are? Some do, but so Bob Boyer and Jay Moore are long-term formal methods people. They have developed a number of theorem provers, and the current ACL2 theorem prover is a derivative of, well, it was their work too, but it was a derivative of some of the earlier provers, some of which they used in the SIP project. Another thing interesting about the SIP project is that this was where the original formulation of Byzantine faults was produced. So it was in this project that Leslie Lamport created the metaphor of Byzantine armies trying to coordinate and communicate in the presence of some arbitrarily disloyal participant. And so that is also relevant to the founding and the development of our team. But while there was some formal methods work involved in this contract and the founder of our group, Ricky Butler, was founder of our this maybe that okay. Ricky Butler was the founder of our group. He inherited the fifth contract near the end, and he became enamored of formal methods, but he was having trouble getting buy-in from management to pursue this further. As you might imagine, government bureaucracy, getting buy-in is often a challenge. But then in the summer of 1987, and I was physically there when this happened, so I am that old, a gentleman from the UK Ministry of Defense's Royal Signals and Radar Establishment at Malvern came and visited NASA Langley. He had met our assistant division chief from NATO meeting and knew that Billy Dog knew that Ricky was interested in formal methods, and this sort of was an opportunity to try and get some support for us pursuing research in this activity. That picture I took this week. That board still lives in my cubicle at Langley. I didn't technically, it's still the property of the Crown, but I think they have lost track of it by now. It came over in a diplomatic house in the late 1980s. And I actually did some code on that thing at one time. That was a long time ago. Anyway, this processor was billed as the first commercially available, formally verified microprocessor. It was a 32-bit architecture, but it was also about 5,000 two-input logic gates. It had, 4 registers, simple ALU, and most of the complexities had to be used in software. But they were selling it as tape because it was formally verified. let's dispel that just because something is formally verified does not mean that it's safe. Uh, in this activity, they did want us to have some independent evaluation of the results. And that sort of became one of our first formal methods contracts that we were starting out to do. And in this one, we asked RFRE who they wanted us to bring into this, and they said Warren Hunt. Warren Hunt had recently done his dissertation at UT Austin. Yeah, not the UT Austin itself. I'm sorry. Yeah, I guess I'm not cool then. So, yeah. So then you'll go. So, so anyway, so Warren had for his dissertation designed his own microprocessor and formally verified it in the field improvement system NQFON, which is the predecessor to ACR2. And so he had certain chops in this area. And so he and Bishop Broad, who were then at a small company called Computational Logic Incorporated, did this report for us as eventually for you to click on. And by and large, they said that yes, there's some good work here, but it doesn't live up to a claim that's fully formally verified. There were some pieces that were not verified and things of that nature. That then ended the commercial process that we did, but it also helped us get our team done. So, so our team was started in 1988. Again, Ricky Butler was the engine behind our team, the motion behind our team. And one of our first hires, I was still a contractor working on something else not related to what I wanted at the time. One of the first hires that Ricky brought in, sitting back there, to a small company called Vision, that was on-site near side of Pennsylvania. And so he was sort of he gave us instant credibility. He already had some known chops in the area, so it was good to bring in someone of that status in the team. We also established a memorandum of understanding with the Royal Signals and Radar establishment and continued working with them for a while. We also initiated a number of contracts with informal methods focused companies. So SOI International, which developed CDS, people who are probably familiar with. Computational Logic Incorporated was a small company in Austin, Texas, that had a significant number of really solid formal methods people then. They had recently completed a tour de force activity called the short stack, where they had hardware, compilers, operating system, all linked together formally in their tool set. But that's a nice little bit of history to look at if you're interested in something like this history. And then the third contact is with a small company in Nicholson, New York, called Odyssey Research Facility. And they've had a number of different formal methods tools for different targeted areas. So we've had all of these contracts in place early on. And a lot of our focus early on was on trying to pair the people with formal methods expertise while trying to build up our own internal formal methods expertise. We paired these contracts with industry and other academic partners as well. We wanted to make sure that our research was grounded in relevant applications. And many of our initial activities were focused on things around digital hardware design verification and verification of fault tolerant properties. Also, about this time, the committee developing RCCA 178 was in progress, and that was sort of the first standard that we got some mention of some methods inserted into, and then there was the author of the original text to that, George Canary, who was in our grant at the time, was the point person on that. Subsequently to that, in the revision to year 178, 178C, there were a number of supplements introduced as well, included the formal method supplement was developed by Kelly Hazel, who was in our group. And they developed formal method supplement DA333, which we then got Collins to produce a material to teach us how to use that in the aviation context, how people in that community could legitimately apply formal methods to gain some form of credit of using formal methods as a design project. So, we've long had this policy and practice of trying to influence the adoption of formal methods, both through building that in-house capabilities, working with both industry and academic partners on formal methods, as well as trying to influence standards. We're going to make a little bit of some other standards we can involve there. Another interesting thing that happened is there are some people in this union that remember what life was like before the government existed. There are some that might not have been born before the existed. The World Wide Web was just getting its start in the early 90s, and Michael Holloway, who's in our group, created a formal methods web page for our research program. That was, I think, the second web page at Mount Langley, and it sort of became a canonical website for people interested in formal methods to point to. So it was, a well put together, had a lot of good tutorial material, as well as connections to various research activities that we had done. Some of the residual pieces of the early web page are visible. There's a link at the bottom of the current site to the first few links. So some of the really old stuff from the early 90s is in the old. The FM now is only 25 years old. That's in the 2000 time frame. And then the current site is, are you the maintenance of that proposal? Yeah. So it's wonderful to have Sega and the thing keeps advancing the sort of the art here. That's to happen. Anyway, so we have that current site. Another thing that we did is we began a series of meetings. This is a descendant of that series. We had the first language formal methods workshop in August of 1990. We proceeded to have a few more through the 90s and 2000s. Then due to various budgetary constraints and loss of funding for our program in the mid 2000s, we didn't do it for a while. And then in 2008, Kristen helped us restore the language formal methods workshop, which then served as the basis for broadening to all of the other master sites, which at that point also had formal methods practitioners. And it became an agency-wide thing. After coming up with Symposium, traces of this from 35 years ago, as August company message. And so here's who was there in August of 1990. This is sort of an audience participation time, and then let's get to close. How many of these people can you recognize? Can you point out any? Yeah. Yes. Yes. Different room there. Yes. Yep. But even then, at this meeting, we had, all of our prime formal methods contracts there. So a number of people from computational logic, a number of people from SLI, a number of people from IT Users Associates. We had a few other academics join us. We had some other government. Sorry? Don Ruffy is there, yes. Don Knight is also in the back row. Yep. Yes, very young contact. This gentleman kneeling closest to me is Gary Cohen, who is with Boeing. The gentleman next to him is Clive Pivot. He is in the Royal Signals and Radar Establishment. So they came to this meeting. His colleague John Kozar is in the back here. We had, yes, yes, he had automatically tinting glasses, so he definitely looked like a Secret Service agent. So, uh, 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 we have Pete Serafini from the FAA. We have Roger Peters, who at that time was on the faculty at University of Nebraska Lincoln, but prior to that, he was with Bendix, then Allied Signal, working on the math architecture, which is the derivative of the architecture. Carl Levitt on the other end was at SOI, originally involved in the SIPS project. At that time, he was a professor at UC Davis, and there were a few of his students mixed into this picture as well. Also had Tom Shin from the University of Michigan. I think he's still there. Uh, he was really more focused in fault tolerance and reliability modeling, not so much in the field of methods. So you did have this nice nitpick people. We do not have anyone from Draco Lab present at this meeting. So subsequent, yeah, John Knight is in the back row, right behind Richard's product, next to Bill Young. Uh, the guy with the beard, Rivas. Yeah, well, he was at Odyssey at the time. Yeah. And then on the other side of Shankar, we talked before, who was at SUNY Albany at the time. Yeah, so it was a nice collection of people. Uh, anyway, so what was I doing at this time? That was about when I started working on my master's here, which was funded and thanks NASA for this. They had a very nice graduate studies program back then. And my master's thesis was verification of fault-tolerant thought synchronization systems, which got reused in a number of subsequent activities related to proofs of fault-tolerant systems. There was a design that I had worked on in the 2000s, early 2000s, called Spider, where we proved all of the fault-tolerant protocols in the laboratory prototypes. In 2008 timeframe, when we started shipping into looking at some space activities, I was tasked to be a fault tolerance consultant on some of the avionics concerns for the what was then called Constellation. So I was involved in looking at the fault tolerance system on the Orion crew capsule, which was flown, and looking at some of the formula analysis of the time-figured Ethernet onboard data network for that, which did have a number of formal methods applications, including properties of that network standing. AS6802, SOE AS6802. So a descendant of this work is currently part of the fault tolerance library in PDF. I'm the only person who knows how to interpret it, which means that I failed the fundamental property of developing a library, which it didn't provide easy reuse for all of unpleasant. And anyway, we are still leveraging that step. All right, and the process that I need to get to this complication. So let's move on to the second step. We're still doing the same basic strategies of, trying to maintain strong in-house teams, work with contracts and research grants, have funding available. We are not married to care improving our group is a fairly care improving heavy group. We've invested a lot of time and effort in PDF, and that allows us to be productive and do things. There's a number of other activities that are underway. So some recent things that we've done in our group in the field improvement playbook was hosting the use of PBS for a number of sort of air traffic management related algorithms that are refocused for dealing with small UOS things. Data was a detection of voice and algorithm that was verified against a separation standard that performance got captured in the DA 365. I recall of these numbers, if I wasn't involved, I recall about the same here. but there was a number of verifications, a number of interesting algorithms here, and the work is continuing ridiculous and derivatives for a number of activities involving small UAS and other applications. Another here including activity that people in our group were involved in. Aaron Butler was sort of the prime person, but Laura also active in this. This was an algorithm that is in use on commercial aircraft now. They had some problems with it in the field and asked us to take a look at it and make sure that we knew how it worked. And so there were a number of issues. One, finding a deficiency in the requirements, fixing that, providing verified algorithms to readers in a number of different implementations, like in fixed point, single precision code, and double precision coding things. All of these things are captured in the VA260 MOC standard. And we've essentially got the full stack from high level requirements down to detailed code implementation embedded in that point. And at this point, I'm going to hand it off to Natasha for this tag team call. I apologize for eating.
We're going to try to make sure we get the right mic. I know there's audio problems. So for everybody out in TV land, if this mic is better, give a thumbs up, or email Abigail or something like that, or you can text me. I'm getting texts too, so that'll reinforce to me that this is something. Okay, people say it's going off. I'm vertically challenged. You're gonna have trouble seeing me. I'm also vocally challenged, so I'm kind of shouting. Wave if I'm not making it to the back of the room. The call, of course, did a magnificent job. I could let him keep going on for the whole hour. I don't need to be here. He knows everything there is to know about NASA and formal methods. He's graciously sharing his time with me. One thing I wanted to add in about PDFs, it's higher order logic. And so it allows for embedding, which is really, really cool if you're into hybrid systems. In the sense that you can essentially take another language and use it as a subset. So you can specify hybrid systems in the way you would like to naturally write them. I'm talking hybrid systems there myself. And that's really, really helpful, especially if you're a control theorist or an engineer who wants to write their specification that way. And I know there are folks in the crowd who've worked on something called Slatic. And I think that we have to see the way that is a great way to specify your hybrid system, do things about it. Also, shout out to Mariano and Marcos for some of the PDF stuff we just talked about. And his stuff we did. I apologize. I'm not going to call out all the people who should. Angry emails in my inbox. That's how you feedback to me. So, as Paul mentioned, we are through improving powerhouse, but we also do other stuff. Kristen is here as well, and she's a fellow model checker. And so model checking is something that NASA does. I'm going to only give you a brief kind of glimpse of some of the other things we do. One of the things is a very nice lossless case study where we were using essentially SOAR and that's a cognitive architecture. We were able to write out in monadic second order logic, essentially second order logic, first order logical quantification of a set. Essentially, rule-based programming was what we're supposed to do. Because essentially, second order logic, you're able to transfer that into an automata. From there, you stick it into equal, which works sometimes automata language. And you can begin doing good. You can begin checking the problem. Other interesting thing about equal, the great thing about equal, it can allow us for stochastic relation. So you can specify stochastic requirements and then check over something that is going to be important. We talk about AI later on, very, very nicely. It foreshadows the I probably should be telling you about what equal does. It's a description language, and the simulator. The simulator I find most bizarre is the substance doesn't matter half the time. Because it's either automatically translate before the default. I get it kind of wrong. And this helps me figure out what did I specify along those requirements. So very, very handy, nice visualizations built in as well. The other thing about this loss with case studies, essentially there's a C2 working group. We talked a little bit about DO365, which is essentially the protect and avoid standard. There's the thing with SC228, which created that. We have a working group, which is looking at the so we are hoping to transition some knowledge to them because that's basically the abundant sprinkles with standards. But also a thing to keep in mind, every single browser is going to have a point of contact. Reputation. I think everyone's had the class that have where we all say, you know, you've got the including model checking the whole gamut. If you've got the requirements wrong, you're going to be in a lot of trouble. And a lot of our mistakes, especially when it comes to implementation, comes with not the requirements quite correct. If you've got the requirements wrong and you're figuring implementing something, just think it's not going to be that's going to be the there's something called PRET, which is formal certification, formal requirements certification tool. It was created by our friend Product News, and it's a very nice framework for the solicitation, formalization, and understanding requirements. There's this language called PRET, which is very open to develop in parallel. Where essentially you have a natural language description of the requirements, but it's only limit certain things and that helps to regularize which can catch of what the constraints will be specified. Using your hierarchical system requirements and what they're indigenous semantics, and we support user understanding, which allows you to essentially visualize what does it mean about say X until Y. You can create a trace of how that could be. I'm guessing that doesn't actually project it as it does in the computer. It's these coming to not there is or of course there's the if we see or delete the history of that kind of thing. So you can take that requirement, you can visualize it, you can see what it means in terms of traces. Again, very helpful for providing answer action before. So it also connects the various other therapies. Oh, what's it called? So essentially, these requirements can do that structured format, we can formalize it, multi out statements, very handy. You can use that to prove things when you don't use it. Other tools which can then take into citing things for some. But essentially, what you can do is you can export to things like other things that choose about the to design verifier as well as code science. Talk about it before the bunch of description. You can literally go from a natural language and treatment fraction. These are the three things that formula to monitor directly. So hopefully that's in the okay. So I just mentioned this mysterious thing called we talked a bit about formal specification, runtime verification, something that's nice and sensible. Probably seen a lot of it. Perhaps some of you are familiar with the lean shock, complex architecture, system under observation. One of them has been formally verified, the other one they did a while back. Monitoring. So if there's no free lunch, it's switched back and forth. You have to level with the function function. That is the level function. You probably need a level switch and between the different no free lunch. The thing there to think about for those who might be if your monitor is super complicated, you can verify that too. You have to make sure that your monitor is correct. The monitor is super complicated. You don't just verifying the monitor as it is verifying your system. It's sort of a structure that lends itself to a monitor, but not being that complicated. So geofence, that complicated controllers. We just want to keep the geofence out of things, verifying the monitor that it's pretty easy. But if you have a very, very complicated envelope protection scheme for an electric motor to take off at 90 degrees, then you don't understand the performance. Whatever you're going to get wrong in the controlling, please keep that into mind. The other thing about monitors that you have to remember, they have to be independent of the system and the observation. So if they're running on the same processor, you have indeed a single system with the runtime monitoring is extremely powerful. Things you're going to want to remember when you use them. Copilot essentially is our only in-house runtime verification framework. It is an absolutely embedded domain, it's a language, it synthesizes your monitor, it deals with embedded systems, generating these literacy monitors. That's part of it. It helps remind things like the Verilog, constant time constant. The benefit of this on the minimum instrumentation of the system. And the monitor can go in and change the thing that it is. Also, very integrated patches. So we talked a little bit about threat and you can specify your requirements in it. Copilot also supports F-Prime, forklift systems, prediction masters, main space systems, backend, so everything. It's like model-based systems engineering. These are MBSE, it supports the use of Bitcoin. Something to chat to Alvin Bigelow about if you're not in the room today, but I believe to be key. So life would not be complete in runtime monitoring if I didn't mention some work by five exclusive on into the field of course. It's interesting things used to forever. It's what they're doing with loss processes actually very, very, very easy. There's even factorization runtime monitoring exceeds the current projection return. But it's really about getting the most out of the trip. Thank you. Create a log file by your they run as a system of observation. It's a shorter memory according to a log. And then you can process it out there. You don't have to worry about doing the computing stuff. Now, of course, what it does require is the domain specific language. You have to extract particular interesting things. Now, file series high contrast. It's a very, very nice, it has a shallow, Python laboratory and how you need to write user properties, which essentially is a combination of basic distributions like based programming. States are parameterized with data, represent facts, and then they're stored in the and then you're differentiating making one of the class, and you can do statistics. And that's the really exciting thing here. That can be embedded as a part of that monitor that you've been into. You can then feed that monitor specific traces, either the use data from simulation or phases. And that's the important. If you can enable on the one with the overhead setting embedded computing something to check. Enables many forms of business apps. We should place the whatever your features, either features of interest. It's really brings home, and I'm doing the badge up explaining the link between runtime verification data. So that you've done is you've taken an online monitoring problem and you turned it into an operating data analysis problem, which you can feed into very much. Each other. And GPS breaks in there that we have some revenue draws.
We're gonna just continue.
We're going to continue. Okay. I'm going to shout at all the things here and hope for the best. And yes, I did not get a text saying shout louder, so I'm going to hope. So we mentioned a couple other things, abstract interpretation, super wonderful. I think Pierre-Loic is somewhere in the audience. So we have some tools related to that and some methods. Precisia, of course, go speak with Cesar and some of the other folks. ICOS, which is out at Ames. I'm looking at my time thing as well. SMT solving, we can go into a little bit more detail, again, offline, as well as static analysis of code, ADA stress and reflow. Static analysis, of course, extremely powerful when you're looking for things like autonomy. So if you are going to actually have a cyber physical system which goes into space, when it's still on the ground, you want the static analysis, the code to be airtight, and then when you send it up, you need to do the runtime or dynamic monitoring. We also do dynamic analysis of code, erase, and a couple of other tools there. It lends itself to simulation, which is also one of the things we've been doing with wildland firefighting. Very nice for visualization of taking in data. They've got certain applications that they like to do a dynamic analysis on as they take these particular programs into the field. Path and branch testing is one of the things that they're looking for in those particular decision-making algorithms. And of course, sim investing. Everyone needs it. We'll talk a little bit about it later again when we hit the AI and ML section of this particular state. The edge case problem, unexplored scenarios, unknown unknowns are going to dominate the next part of our talk as we delve into what the future of what NASA is looking at and what formal methods really can be leveraged for as we go forward. So let me do this. So future. So safety oriented. I'm going to talk about AI ML first, but Darren did such a good job. I want you to kind of forget about how good his talk was. Then I'll flip into AI ML. Don't forget, autonomy. I can have an AI or machine learning helper, or essentially a assist or a recommendation tool, which has nothing to do with autonomy. It recommends what shoes I should be buying from Amazon, or it recommends, what decision maybe I want to take as a human who's attempting to manage a contingency. Similarly, and this one is a little bit more controversial, autonomy does not require the use of AI. And this is a NASA position simply because we have had autonomous missions since the 60s. We have sent Pioneer up into space. How do I know that it is autonomous? Pioneers, I think 4 and 5, only had transmitters, no receivers. So once it was up there, you could not send commands to it. Now, it didn't do anything fancy. It went slingshotting around the moon, did some controls, did some attitude adjustment, but still, by the book, by definition for ICAO, that is an autonomous mission. So the two words are not the same thing. Please remember that. So when I talk about cyber physical systems, human-centered ones, and the challenges related to autonomy, I'm not thinking about AI right now. I'm just thinking about the autonomy. One of the things that we're obviously looking at is the human role allocation. In space, as they say, autonomy means something slightly different. It is a remote operation. There's a human on the ground. There's a system way out in space. There's a time lag. And that time lag can be minutes, can be hours, depending on where that thing is. And so you can no longer do inner loop or even medium loop control. So essentially, this is what they're thinking of when they say autonomy. So that authority, responsibility, allocation is paramount in their mind. If you're having to make decisions on what to do in the face of an anomaly, that's huge, because whilst it's not necessarily safety critical if there's no crew on board, you can, lose billions and billions upon dollars in mission critical hardware, software, and of course the science in that mission. Bounding behaviors. Okay, I'm taking too long here. This is my soapbox, as you can see. Bounding behaviors. So for on the ground eVTOLs, we don't know how these vehicles work. Essentially, trying to couple an uncertain environment along with dynamics, which we are not well versed in. Envelope expansion for some of these vehicle configurations is not done yet. We've got a host of things to worry about. There's contingency management, fault containment. Paul talked very much about these architectures. Do you feel silent? Do you feel safe? What is the right strategy there? Heterogeneous vehicles, so interactions between things that are not the same. If you're a general aviation pilot and you're flying with an eVTOL, there are different capability levels between those two vehicles to think about. Similarly, equipment on board may be of different years and different makes, and mixed ConOps. These things fly differently. Trusted decision-making, I think we've all talked about that. There's a shifting locus of control where decisions formerly made by humans, such as safety critical decisions, are now being offshored potentially onto automated systems. So how, again, do you go about guaranteeing their safety? Operational approval, certification, public trust. I'm sure anybody here could give hour-long presentation on them. But these are challenges. The first one you can see, V and V, that one is the one where formal methods can make a big difference. Similarly, certification, that one, formal methods we're hoping can make a big difference. We talked about DO 333, the formal method supplement, to begin your dialogue with the FAA, perhaps, if you wish to use formal methods. So I've been chatting about work done across NASA. I could not, give a talk without talking about the work done by Julia Badger out at JSC. They've done some pioneering work for space-based applications, essentially looking at distributed hierarchical frameworks for spacecraft autonomy. It's actually similar to work done at Collins, again, another Collins shout out, where you're essentially looking at integrating contract-based reasoning across distributed hierarchies. And I should probably talk about that work a little bit too. I'll do that off the cuff. But as we mentioned, we've got these future space missions. We've got variable levels of autonomy. So imagine you're something in geosynchronous orbit, perhaps, or midway between the Earth and the Moon. Sometimes, a crew capsule comes and docks with you, and sometimes it doesn't. So sometimes you're crewed, sometimes you're not. Variable levels of autonomy. So the paradigm under which that station, I'm not going to call it by name because who knows what it's called, the paradigm under which it operates, sometimes it must be fully autonomous, other times it has to be human rated, and of course can have repairs or crew interaction occur. Now, of course, if you're ever populated by a human, you always have to be human rated, but that's a different argument that Paul and I will have later. So what is this distributed hierarchical framework? How does it enable essentially assuring these multiple paradigms of autonomy in the same bucket? Essentially looks at a component-based architecture approach, providing interfaces and structures to the developing autonomous technologies. So you're automating, or your autonomy is by function. So this particular function is autonomous sometimes when there's no crew on board, and it can be, of course, non-autonomous or have an increasingly autonomous paradigm when there is a human either assisting it. If you remember Tom Sheridan's 10 different essentially levels of human machine interaction, you can be at a 7, which essentially is human machine essentially pairing, but the human has the override, and then you can go to a 10 and that human is no longer there. But you have to verify it all under the same framework. So essentially you have to respect the independence of modules, but also model the interconnectedness between them. So you're enforcing a strict command and telemetry flow through a systems engineering tool, and you have a path to formal analysis to assume guarantee contracts, as long as your components can be individually verified. So those autonomous functions also have to be proven to be correct under each of the paradigms you are exercising them. So the inclusion of this contract-based design encourages these verification methodologies we can bring in. I believe they brought in SMT solving, and I want to say model checking, but I'll have to make sure that I got that right to support their component level verification. And it facilitates the logging of data. So we just finished talking about logs, getting the most out of your traces. Something to think about, self-driving cars, we say millions and billions of miles. We don't have lots of operational data for space applications. As they say, they're one-offs, they're tailored, and they have limited lifespans. So getting the most bang for your buck out of how much you're doing up there is really, really important. Generalizing from small n, they call it. And so they have this logging ability to be lightweight accumulator gathering efficiently in real time or logger software, which then allows them to go back and apply some of the tools and techniques at a JPL to attempt to see what they should and shouldn't be monitoring during different variable autonomy periods. You can see folks looking confused. Come up and we'll chat afterwards, and I'll defer all the hard questions to Julia. And it's a great collaboration with the JPL as well, with Steve Penn's group, and we'll talk about that a little bit later. So again, I'm going to look poor in comparison to the amazing talk that Darren gave. I was up at 5:30 in order to get my computer running to see it on Wednesday. I really enjoyed it. You'll see my little spin on the problem of AI and ML and how formal verification can help out. Obviously, in my opinion, the inability to establish appropriate assurance for AI/ML components leaves us unable to effectively manage their risk. It may drive cost of development very high. It may delay adoption of AI or ML at scale and can result in unknown or unmanageable risks. So the goal really becomes what constitutes sufficient scientific, I probably shouldn't use that word, sufficient evidence. What constitutes sufficient evidence to substantiate a safety claim related to this particular component performing a safety critical function? And you'll see on the far side a variant of a diagram you'll have already seen with an extra circles. Data sciences. Some folks believe that circle should be entirely on the three nested circles. Mikunjosa and I have had interesting conversations on that. There may be portions of data sciences which are outside the AI/ML realm. And just so you know, when I say AI, I'm really thinking of machines that can learn, reason, and potentially act for themselves. But ML is a little bit more rigorous there. The use of statistical techniques to analyze data and create algorithms that can generalize to unseen data without explicit programming. So again, you give it some data and then it's able to interpolate or extrapolate. And you don't have to program those cases. So ML is really what I'm saying as we go through these slides. All right, this one you probably don't need as much. It again reinforces some of the points that were made on Wednesday's excellent talk. You know, what are our problems with these ML components? What is the criteria that you're attempting to test for? So if you're going to say, okay, I can test my way out of this hole, the complexity of these particular implementations, machine learning implementations, I believe the latest phrase is unit of training, which is basically looking at the data and all the activities necessary to support the machine learning implementation of the particular requirement in question. What is the right test? For a screw, I know the right test is, can I bend it? When does it break? For a machine learning component, am I looking at the F1 score? If it's a picture with multiple things in it, is it intersection over union? What is the thing that you really need to test about it or determine about it to know that it's doing what you want it to do? Feasibility of any sort of testing regimen. We talked a little bit about coverage. So the first requirement was a little bit about traceability. We've got a high level requirement we're attempting to implement. That high level requirement, when you actually have to bring it down to the specification of that unit of training, what is that translation? We don't know how to trace that down. Feasibility of testing, what does it mean for coverage? I twist my screw a little bit, 1 pound of force, 10 pounds of force, 20 pounds of force. I draw a curve. I don't have to test every point. What does coverage mean in this case? And that is an open question. We actually are doing some lovely work with JPL, Steve Chen's group, with Alessandro Pinto and a couple of other guys, trying to figure out what we should be thinking of. And of course, lastly, process and product correlation. We talked a lot about standards, 178C, 254, and other things. Rigorous processes often yield better products, but correlation is not causation. So what are the right particular processes you want to be exercising for your unit of training? Open questions. So how does formal methods help? Many, many, many ways. I point to our wonderful friends at Collins, who I believe have the first special condition for a machine learning component. Yay for them. They're doing great stuff. Formal methods is part of a regimen. So testing is indispensable. You're still going to have to do some testing. Simulation is also going to be super helpful. Validation of assumptions, interfaces, and constraints. Feasibility or satisfiability analysis of temporal behavior. Simulation actually probably gets you further than some of the formal methods analysis there. Again, within the bounds of the validation of that simulation. Verification of code implementation, and of course, checking components, aggregate to get the right system level behaviors. Simulation's a part of your toolbox. However, it's insufficient because of model inaccuracy, incorrect assumptions, unknown unknowns, just like testing is insufficient because we have no idea what coverage metric we're trying to hit. Formal methods is going to be able to provide you guarantees for these components. The trick there, of course, is the complexity of the component. Again, just like with the monitoring, you need to have a good model of that unit of training. How do you validate that model? How do you know your data is sufficient as you create that model? So there's a couple of questions there that do need to be answered. And again, not very, very satisfactory. What I am going to do is I'm going to show you one of the tools, again, in space. That's where NASA is leading in terms of machine learning deployment. Again, our friends at JPL actually have deployed planners in space, Steve Chen's group, essentially, which have machine learning as their backbone. Now, it had to buy its way on the vehicle and sit down with Steve with a beverage of his choice, and he'll tell you the story. But one of the things that can help, Plexel, which is a lovely planning and execution language, basically allows you to look at the plans you're generating. Plexel 5 is the NASA Langley developed formal operational semantics of Plexel. Plexel itself is developed at NASA Ames. However, we are working with them to help formalize their language as well. And Plexel 5 will allow you to provide that reference implementation of the Plexel executive. The Plexel executive is such that when you are wanting to upload your plan, you don't have to compile it. And that's very valuable because obviously if you have to compile something on the thing which is flying in space, you need to do a lot more for it to get it onto the vehicle. Since there's no compile necessary, you can upload these plans, these Plexel plans, much, much more quickly, a faster pace, which allows you to be clearly more reactive. Plexel 5 allows you to use theorem proving and model checking for the formal verifications of the plan and the plan executions. So as well, you can imagine getting the executive right is very important, and making sure your plans, of course, do not endanger mission critical operations is extremely important too. And so on the ground, verifiable, correct planning, and then there's the runtime verification component. And I'm sure I'm mangling it. Please see Cesar Munoz to clarify all the mistakes I'm making. But essentially from Plexel, you can go to your Plexel executive. From there, you can create a runtime monitor as it runs. That runtime monitor, of course, is fed into by Plexel 5, which is the Langley component. All right, I'm almost done, and I'm looking at the time. The flip side, using AI or ML for formal verification. So that's actually pretty cool. Essentially, there's some very nice uses for it. It can help a specifier in writing their specification. So if you've got templates, it's very nice for something to be able to suggest to you a template. So if you write a certain type of a function or a certain type of structure very frequently, it'll be lovely if it just called that up for you. Suggesting and accessing it. PBS, as Paul says, is not as easy to maneuver your way through and find the right lemma or the right template as you might think, unless you're a person who's been there from the 70s and know where they all are. So searching for these particular templates or tools, models, or techniques is also something that machine learning can do for you. If it digested the PBS library, it probably has a better idea of where that specific lemma you can't just quite remember is lurking. It can also potentially suggest a step in a proof. Now, keep in mind, a human has to check it. I use the analogy, it's very similar to how we use AI or ML in design of aircraft, basically for optimization. Anything that a human would have to guess to start. So, the optimization process, you guess that initial point and then you attempt to optimize. Anything where it's a guess at the beginning, machine learning can probably look to all the other proofs which are similar to yours and say, hey, I see this as a next step frequently. The other big thing, proof repair and change management. So you change a little thing in a lemma here, you change a little thing in a proof there, a module there, and everything breaks in PDS. We've all had that kind of a day. Machine learning can firstly check to see, oh wow, did everything break, which is something you probably want to know. And then it can suggest structures by which your proof can be repaired. So you have a proof, you have multiple cases, you add an extra case. Well, if this case is similar to other cases, perhaps it can suggest the structure of those other cases which you have previously proved and how it might best hook into your architecture. So again, 3 things by which you can potentially use machine learning in order to help out in informal methods there. So writing a specification, searching for information, and proof repair or change management is how I call that. I'll end up with a couple of remaining open challenges. Scalability and complexity, again, this is something we're all very well aware of. It's not just the scalability of the particular tool you're using, it's also performing verification at scale. So if you want to parallelize something, often we don't have a very good way of hooking together multiple versions of our theorem prover, which is attempting to provide little bite-sized pieces of your proof, especially model checking. That's the big one where you can also see that there. Time and cost constraints, as well as modeling and abstraction. Education and training. So when we hear that, we often say, oh yeah, we've got to train up staff. Indeed, that is something that needs to happen, and big companies don't like paying to train undergrads to do this. There's the education and training of the formal methods tool and technique developers. How do you create a product that people are going to want to use or that is easy for people to take up? So I think there's a happy medium there, a way to try to see, okay, this is as much knowledge that my user is going to have. What can I do to enable the uptake of this particular product? And then ease of use and interpretability. Model checking is the obvious example. It throws you a counterexample. I don't know what that counterexample means. Sometimes that counterexample is spurious. How can I check? How can I interpret that? Do I have to be an expert, not only in the system, but the tool to understand whether or not that is a false or ambiguous result? So I'll just summarize. This is a list of thoughts. Formal methods is really great. NASA has served as both a nexus and a catalyst of formal methods in the community from the 70s all the way on down. Also, keep in mind, formal methods, whilst an enabler, it's not a panacea, but it can increase confidence in a product's safety and very useful for consistency checks, and it has to be applied judiciously. Some of the biggest failures we have in industry is because we've tackled the wrong problems or we've tackled the wrong scale of problems. So really think about carefully when you want to apply formal methods, what you're applying it to and for what duration. An incomplete list of thank yous again. Please, angry emails. This is a small list of the people who I've just talked to, gotten information from, synthesized this talk. We've synthesized this talk from, obviously, without the entire formal methods team across NASA, there would be no effective NASA throughout the ages talk at all. So this is just thank yous to everyone out there. These are people at NASA. I'm not even talking about the general community. We've had some wonderful work with Collins just recently looking at taking things from cognitive architectures into Amaze, AADL agree, and then all the way down into new XMV, and then proving out new human machine teaming paradigms. Work like that, where NASA serves as a catalyst. I think that's some of our greatest contributions. And we look forward to hearing feedback from you on how we can continue to vitalize this community. And with that, I'll stop for questions and thank again the program committee for inviting us to speak.
So definitely want to have some time to take some questions. We do have, for the people online, whoever answers the question, you will need to repeat the question because that's the only way we're picking up audio today. So are there any questions for Paul and Natasha?
So thanks very much. It's been very fun to see you talk in person. It's amazing what's there. So I was in a high contract with Klaus, and it's sent a photo of the slide, and he says he wanted to make the point. He said, first of all, he commented on your slide and said, great. He said we're actually using high contract online monitor to navigate the research project. So he says also now it's the Scala version. It says they can be used for online, just not if it is a BMW overtaking on the journal.
Yes, thank you, Klaus, for the clarification. I was pulling this information from the paper that you and Alwyn Goodlow wrote. So go fight with Alwyn. I'm gonna duck and hide behind him.
Yeah, us, if you like just coming, like maybe 6 months or something like that. So how do you, like, what's the vision on, like, the research station for to keep pace with that evolving landscape, like, and also to verification of this AI, things at scale?
So I'll repeat the question just to make sure I've got it right. I'm a little bit jet lagged, as you can tell. So how is formal methods going to keep pace with the fast changing world of AI, and how to address AI at scale? So here's the thing to think about, as Darren rightly calls these units of training. The AI component you're looking at is actually often small. Now, I'm not talking about, okay, how would I verify a large language model? Because in space and on an aircraft, I'm probably not going to put a large language model on my plane. But if I have a small implementation of an AI component, in some ways you can just think of it as boxed out, almost like COTS. So I'm not exactly sure how the internals are evolving so quickly, but if I only consider its behavior at the interface, that's really what I'm looking to prove things over. So the fidelity of the model of perhaps that underlying neural network is not the biggest thing I'm worried about. It's how do I capture the properties that I want to verify over it? And that too is tricky because you do need to think about the requirements on that particular component. But thinking about those requirements is divorced from that neural network implementation, which may be evolving. So I see the real work being in how do you come up with the traceability of those requirements. If I have that kind of high level requirement, which is implementation agnostic, and then I turn it into an implementation specific, an AI specific requirement, that's where I would concentrate my formal methods power on that traceability. How do I make sure I got that translation right? But I'm sure Darren and other folks have more insightful things than my fever dream thoughts. Paul, did you have anything?
And very easy to do that. And I bring my notes about that. I expected in natural language. There was text, and that's the most difficult part of these of the development. And then purchases into default. Then there's possibility. So after do you have a battery and then going to be read by? If what you affect speaks out, actually makes sense for the length.
You want me to start and you to finish, or? So yeah, so you have, so we worked with Fred on a lovely project. Aaron was a part of it when Dimitra was still there, doing exactly what you were describing. So we were working with Mike Fury's group, who were doing performance envelope expansion for an eVTOL. Writing the requirements from their point of view meant something very different than capturing them in Fret. And so this required iteration. So they'd say, yes, okay, we've got this easy fly control algorithm. We make the transition from vertical flight to hovering flight by passing through 3 different control regimes. It was like, so Dimitra, how do I capture that? And so she would come up with, A until B until C. And then she would run a little simulation. And then we'd have to go back around, sit with Mike Fury and John Kaneshigi as, is this the type of behavior you want to see? And they go, no, where did you get that from what I said? No, this is a pusher prop. This is, no. Let's start again. And so that's a human oriented task. I don't see particularly an easy way to automate or somehow formalize that away. That you have to talk to John and Mike because they know what they mean in that particular fashion. All right, everybody, grab your cookies or sandwiches. Come on. We've got an exciting talk. Please. Once. Grab that little extra bit of coffee. Keep you young and vital. So you can see before I came to NASA, even as a contractor, I was a professor. So mentally hurting you all into your Okay. So this is the most amount of attention I ever get from the class anyways, so I'm just gonna jump right in so we can get started. We've got a wonderful session on runtime verification coming up. I am privileged to introduce our first speaker, Alexis Orant. She will be talking about towards a safe, verified runtime monitor for embedded systems, R2U2 in embedded run. Please go ahead, Alexis.
Thank you for the introduction. Your keynote actually kind of leads into my presentation. So when we think of runtime monitors, there's really two main applications or use cases. So first, you can think of offline runtime monitoring, where we've previously collected data and we are taking that data and running it through runtime monitor after the fact to see whether it was satisfying or violating a set of system properties. And then on the other end, we have online runtime monitoring, where we're deploying the runtime monitors actually on the system and detecting in real time, are we satisfying or violating a set or system requirement. And so in this talk, we are focusing on the problem of online runtime verification. So when we are deploying these runtime monitors on the actual system, we have to fit within the target system timing and memory constraints in order to produce verdicts in real time, which is feasible for this real-time deployment. Now, often when we are dealing with these types of spacecraft or aircraft, they often will also include, maybe you have to deploy on a resource constrained system like a microcontroller, or maybe an. And so we need these runtime monitors to have really minimal resource overhead you deploy on these types of systems. Now, runtime monitors, they have to be feasible to run these systems, as well as they have to produce correct results. They're producing incorrect results, well, that negatively affects the system. That is against the idea of what runtime monitors are supposed to do. They're supposed to be your system and help you verify your system in real time. That leads us to, where does R2U2? The R2U2 stands for Reliable, Responsive, and Intrusive Unit. It has previously already been known for its real-time guarantees and resource-aware architecture in such a way that it has already been successfully deployed on several resource-constrained real-time systems, such as Iowa State SAT-1, Iowa State Novosomium Sun and Rocket, NASA's Robonaut 2, NASA's Lunar Gateway Vehicle System Manager, and many other systems. So R2U2 can already be deployed as a runtime monitor on embedded systems. So what did we really look at within this work? So let's go back to the title of this talk. So we are moving towards a runtime monitor for embedded systems. So how can we improve R2U2 to continue its support for deployment in embedded systems? Can we reduce its resource overhead to make it even more amicable to these embedded systems? And then we're also moving towards verified runtime monitor. So how can we guarantee that the results that this runtime monitor is producing are correct? Perhaps you've heard the question before, who watches the monitor? So we have runtime monitor, it's watching the system, checking in real time whether the system is adhering or violating a set of system requirements. Who's making sure the monitor is actually behaving correctly? No one really. We need to make sure that it's correct when we are deploying it. And so you look at ways to prove that R2U2 will in fact produce correct results. And lastly, we look at towards a safe, verified runtime monitor. So can we develop R2U2 in a language that promotes memory safety and allows us to target these embedded systems? So that leads to R2U2 and embedded runs. So before I get into the bulk of what we did, it's important to kind of understand how R2U2 works under the hood. So we have the configuration compiler for property organization, C2PO. C2PO will take a C2PO specification as input. C2PO itself is just a Python compiler. And these specifications will include Boolean expressions or temporal logic formulas, and it will decompose them into an abstract syntax tree. So this abstract syntax tree will then be output from C2PO as a list of assembly style instructions for R2U2 to reason over. So as RTU2 sequentially iterates over these instructions, each instruction directly encodes a node in the abstract syntax tree. So as we iterate sequentially, we're really propagating up this abstract syntax tree. So RTU2 is reasoning over the RTU2 instructions, which is kind of like an intermediary representation of our specs. And we'll take the input data stream and produce output variables. Inside of RTU2, this abstract syntax tree, each node is stored as a shared connection queue. So it will compute in the vertex timestamp tuples according to the operator, and then it will store it appropriately and size appropriately. So the parent nodes can use the values to its operation as a result get propagated. So into the work we did, it's important to note that RT2 was previously before this work only written in C for software realization. Many of you, I'm sure, are aware, it has memory safety liability. We saw this even within our own implementation of RT2. We could write specs that would require more memory than what we originally anticipated. So two things could happen. There could have seg fault, or after we just get erroneous results back. It's reading some random space in memory. And this is not okay for runtime monitoring. We want to make sure that they are producing these correct results. And so in general, all of these programs are being transported to embedded Rust. Embedded Rust has become a popular alternative because it eradicates using memory safety vulnerability. So that's what we did. We took our previous C version and manually transpiled to fake embedded Rust. If you want to note here that this works, RT2 now is the only runtime monitoring tool out there that is available in embedded Rust. Now, there are two other runtime verification tools, RT-Lola and Tesla, that do provide Rust implementation, but they are written in such a way that they actually require Rust standard library and require an operating system. Not equivalent to embedded Rust. It is not applicable on their bare metal environments, such as a microcontroller. So that really signifies what we've done here is we're making sure RT2 is still applicable to these really simple systems, like those microcontrollers. Now, as we manually transpiled from C to embedded Rust, we really looked at the internal architecture and how can we reduce the resource overhead. And so first, we looked at the past time monitoring of RT2. So previously, before this work, the future time engine used mission time linear temporal logic, or MLTL, for its temporal logic specifications. Now, if we wanted to encode a past time property, we could use past time metric temporal logic, which metric temporal logic and mission time linear temporal logic have semantic differences, specifically how we deal with the interval on operators. If the lower bound is not zero. So there's this semantic difference happening between the future time and the past time, and there's inconsistency within the projects. Additionally, the past time was not using the shared connection queue that I just discussed. They were still using single read queues, which actually required more memory resources to store the required buffer's. So now in this work, we have now for the first time formally defined past time mission time linear temporal logic, which directly reflects what we do in future time, but for past time. So there's no weird semantic difference. It's different than past time. And then with this reformalization, we also encode past time MLTL operators with the shared connection queues. And we'll see an example shortly of how we increase the memory resources by using shared connection. So if we looked at these operators, we also looked at how RT2 is actually encoding these operators. So it doesn't actually encode all the operators, all the Boolean connectors and temporal logic operators. It only does a subset, and then the rest are represented by a semantic code. So let's just take a look at the top of this table. So previously, in the previous C version, we directly encoded the negation and the AND operator. But to get OR, we had to use De Morgan's law, required reaction equations. Yeah, reaction nodes and abstract syntax tree, reactor instructions, a lot of extra memory that we have to store. And so we looked at, can we provide a more optimal direct encoding? And so now we encode both and the org, getting rid of the Morgan's law. And there's a couple more things in this table. If we look at the bottom here, for task time previously, because there's task time metric temporal logic that doesn't traditionally have a trigger operator. So it wasn't included in R2. But with task time, mission time linear temporal logic, it would, because you're reflecting how to work in future time, and mission time linear temporal logic, which includes both until and release. So it would make sense in task time, we would have sense and trigger. You also notice here, there are only certain ones on high level. Those are the ones that we directly encoded. We still didn't directly encode all operators. And there's a couple reasons. For example, if you look at future and globally, that can easily be encoded with until and release without any extra instructions. And so see that it doesn't make sense to add extra logic, which would require resources, as well as it allows our code to be a little bit more maintainable and allow us to really take a lot of time in verifying those more complex operators. So last, we looked at the actual instruction format. So as I said, each shared connection queue is represented as an instruction that our Q2 reads. We really looked at what was the instruction format, what was being stored, how many bytes, what was the size, and we did a more minimal encoding. So for Booleanizer instructions, which can take integers and floats as inputs, and might do some addition or multiplication, characters, or Boolean, we were able to decrease the size of these instructions from 28 to 25. For temporal logic instructions, which encode Boolean connectives and those temporal operators, we were able to decrease it from 28 to 16 bytes. Now, this is pretty low-hanging fruit, to define this optimization, but it is rather significant. So we compared the previous C version, which is version 3.0, noted here in yellow, against the optimizations for our optimized version, noted here in blue. And we tested this against 4 different benchmarks. We have the SciSat-1 and the sounding rocket case study that I mentioned before, where our teaching is actually deployed. And then we have an MLTL random and a task time MLTL random benchmark. And we can see across the board that our instruction size increased at least 2 times across all these benchmarks. And that's because, one, we have less instructions because we have a more optimal encoding, as well as increase the size of the instruction. We see a similar behavior with our shared connection queues because we have less instructions, we use all those extra negations. There's less nodes, but only there's less shared connection queue spots we have to display. And here you will see that for task time MLTL, we see a more significant increase. This is because we got rid of the archaic single read queues that we used previously and replaced it with our shared connection queue architecture. And lastly, we look at latency. You can see in latency improved quite a bit. This is mostly because we have less instructions to operate over, so you can do them faster. As well as we actually optimize the algorithms. But if you look at the task time MLTL random benchmark, this one decreased the least. And this is because previously it was actually task time metric temporal logic, and we had actually directly encoded all of those operators. So we're not seeing as much of a benefit there. And then to do task time MLTL correctly and not delay results, I'll talk about why we shouldn't delay results a little bit. Actually, is a little bit more effective than what we've done previously. So overall, we decreased both memory and the timing resources of R2. Then we look at, well, we also provide guarantees of correctness of R2. And so it's important to remember that R2 can take as input any MLTL or task time MLTL spec. At runtime, it just reads in those instructions, and so it interprets those at runtime. And so this makes R2 more challenging and problematic to verify, as worded by the developers of low law runtime. That doesn't mean we didn't have success doing so. And so we started with constructed groups for all of our teachers operators, as well as the read and write operations for the shared collection. Then we also did normal testing. So we did like regression testing over a wide range of formulas that we've seen in real use case studies, as well as we did some exhaustive testing, or rather semi-exhaustive testing, where we tested every possible MLPL formula up to a specified nesting depth and interval length with a specified space as well. And so we were able to exhaustively test up to a certain point, which took about a day at least to run these exhaustive tests. As well as then we also did code verification to verify the correctness of our Rust community. We started by examining and utilizing so Krusty and Barrett, which are all deductive code verification tools for Rust. But we ultimately chose Barrett. We actually found that Crusoe and Krusty, we could not encode everything we needed to for the complexity of these temporal operators. So with the until and the release, we simply could not specify what we needed to with Crusoe and Krusty. So if you have heard of Barrett before, it's actually pretty cool. It directly encodes Rust code and your Rust in your Barrett contract. You can have them submitted for input into D3. And because it's doing this direct encoding, it's actually very, very fast. So we've composed pre and post conditions for 25 of our teaching operators. And this included about 487 lines of code. So for our Boolean and temporal operators, we made sure that our pre and post conditions match what we had set in the and constructed groups. This is a very simple example of our not operator. You want to see our until and release, it's quite a bit more extensive. I have a link at the end of this. And then for our Booleanizer operators, what I thought was cool about Barrett is it actually automatically detected several places where we had underflow and overflow possible. So as I briefly mentioned before, in the Booleanizer, we could have integer or float inputs and like add them or multiply them before we do some sort of comparison. So when we add, multiply, divide, flow and overflow feature. So now we have safe saturating operations, and we properly detect whether underflow or overflow would occur, and we actually return this flag to the user. Now, what I thought was kind of cool and not expected about Barrett is I actually used it to help reduce and optimize our algorithm. Because it is super fast, and I knew exactly what until and release to do, like semantics are very well defined, I was able to write my pre and post conditions, and I worked with my algorithm, really check my different conditions and really optimize for it. And so I was able to use Barrett in almost like a test-driven development approach using formal methods. So I thought that was really cool. And really nice that Barrett is just very, very fast. Like it takes a second. As long as it takes you to compile your Rust program, that's how fast Barrett is. I do need to note, Barrett is not perfect. It doesn't support floats, modular operations, and certain root references. So you can't verify all of our Q2. And that's why we're only able to verify 25 of our Q2 operators. So any of the float operations inside of our Q2, we weren't able to verify. This is still a large bulk of our Q2 that we were able to use Barrett to verify our Rust implementation. And with our hand constructed proofs, our testing, and our code verification, we found bugs in our previous version. So I do want to note that these bugs actually didn't result in incorrect verdicts, but rather they led to unnecessary memory usage, delayed verdict, and consistency between tasks and people. So that with the shared connection queues, there was actually a bug in the previous version where each of the shared connection queues for a temporal operator required 2 extra slots, simply to cover a bug with how the algorithm was wrong and how we were reading and writing in a circular chain. So once we were able to fix that, we have 2 extra slots that we didn't need anymore. We could just remove them. So that's also a reason why we saw that great dip in the shared connection to the side. Now with runtime monitoring, we never want to delay results. We want to give those results as quickly as possible as to not limit mitigation actions, and to not delay alerting the user whether we are satisfying the quality properly. So with the until operator, in the previous algorithm, we actually had to wait for both children to be known. So we had to know both the left-hand side and the right-hand side of the until operator. But actually, for example, in this specification here, if we know the right-hand side is true at the lower bound of the until, which is at that 2, if we know it's already true at 2, it's just true. There's no reason for us to wait for that globally from 0 to 3.5. So let's determine the result. Why are we delaying quickly? And lastly, as we discussed before, our past time monitoring had encoded past time metric temporal logic, which did not match with what our future time engine was. And so we replaced that with a past time mission time linear. Really straight, we can really target embedded systems. We deployed it on a microcontroller. So this is a very small microcontroller. This is an FPM32 F3 discovery board. As you can see, it only has 48 megabit system clock, 256 kilobytes of flash memory, and 48 kilobytes of RAM. That is all the memory on board. So when I was talking before about the instruction size and shared connection key size, that was in the scale of kilobytes. When we're targeting these types of systems, it really does matter. And so we were able to run this little demo as you can see. So when the green LED shows up, that means that once between now and the past 5 seconds, I had pressed the button. And when the red LED turns on, that means globally from now in the future 5 seconds, I you can see that in MLTL, we encoded that with the interval from 0 to 500, and we ran R2 at a frequency of 10 milliseconds. This is how we got that. That's a cute, cool little demo. We also ran the original benchmarks. We could see that all of them were feasible. We had no issues deploying it on this microcontroller. We'll see here that the latency per time step is in milliseconds. Previously, when I showed you that latency with this captured laptop, it was in microseconds. It's definitely quite a bit slower, which makes sense given that we only have a 48 megahertz system clock. But this millisecond still indicates that we can still have real-time performance, even when we target something that's not. So in conclusion, we have a new implementation of R2 in Rust. We significantly decreased the previous resource overhead, as well as provide a guarantee of correctness through hanging proofs, testing, and code verification. If you really want to read all of the main constructed proofs and use that QR code, as well as you can see all of our abilities. We also have publicly available crates on crates.io where you can install using the cargo dependency library for Rust. We have R224, which we can pull directly into the projects. It has a nice API to how to interact. We also have R22 CLI, which builds on R224 to allow you to put it in a command line interface on your computer. I also want to note, since this paper, we did apply those optimizations I talked about back to the C version, which is now publicly available on our GitHub. Future work, we plan to incorporate more code verification as Varus continues to develop. So nice about Varus is they're continuously developing. They have a lot of funding. They're releasing new features on a daily basis. So as they release new features, we plan to incorporate more code verification and other Rust implementation. Also, we did hand constructed proofs, which is a good step forward, but obviously hand constructed proofs are not the best thing. So we're also looking at formalizing R2 proofs of assistant. But with Isabel, this is a big challenge with how we have to share connection queues, we've got our syntax tree, we have stream-based reasoning. It is something we are actively looking and trying to do, as well as we want to do more intuitive automatic test generation to further validate R2. So we did semi-exhaustive testing. Can we be a little bit smarter about it and then have a wider range of specifications and validate it against R2 against the board. So that is everything I have for my presentation, and I will now open the questions.
So excellent talk. Let's see the first question.
Thanks very much for this. I think this is great work and exactly the type of thing we should all be doing. I was curious, you said that the Rust implementation, you're transpiling from the C, is that correct?
Manual, so I try to convert as fast as I could from C to Rust. So obviously, automatic transpilers are just not there yet.
Yeah, I mean, why transpile? Why not go like from the, like you have, I don't know exactly which level would make the most sense to do it at, but if you do it at the AST level or if you do it at the instruction level, but like why not go back a step?
I guess just to make sure I had an exact copy of my C version, that I wasn't involving extra errors, and then I can match them up and then look at my. And then I eventually converted it back to the C. Thanks.
Thank you, Alexi. Very nice work. I'm wondering, when you have like a lot of nesting, what is the impact on the memory footprint? Like, is it linear or more than linear in the number of nesting? How much does it depend on the window, the Windows length of the operator?
So there's an equation that we have on how we shared the set or size of shared connections used. So it really looks at sibling nodes, and it's quite complex. If you want to read the paper, there's an actual algorithm, and we have a proof in the previous paper. So sometimes it will increase a lot, sometimes not. We have just a simple until operator with nothing else, and we just increase the interval size to whatever. It doesn't increase the memory at all. But if we take that and it with something else, so we can have the buffer results, we have to re-verify and increase output for every time step. That's when it can require more memory. So more complex specifications combined with those increased memory.
Thank you.
Further questions in the room for Alexi?
Thank you. No, I really enjoyed your talk. I think this is great work. And so my question is maybe a little orthogonal, but I've worked with, because you were using Varus, I've worked with Spark Ada, which is very similar from the Ada language. And so I was curious your experience working with Varus when you're proving something about a function, the pre and post conditions, and it fails to verify. Like, how good is the feedback from Varus? Like, is it useful for finding where the error is, or do you just kind of get like, hey, there's something wrong? And so you know there's something wrong, but you have to go kind of figure out what it is on your own. When I did this paper, pretty much just tells you something's wrong. It might provide a little bit of a back trace, but I know they're currently actually working on providing more detail. And as things get verified, they'll actually output a full proof. So that's the nice thing about Varus. They are working on all of the cool things that we would want. Yeah, I suspect it'll get better over time. Okay, thank you.
Further questions in the room? I'll ask a very quick question as we get ready to transition speakers. So very lovely. You mentioned you're going to formalize those handwritten proofs. What are you looking for in your theorem prover that will help best formalize your proofs? Why, Isabel?
This is about any part of our lab group.
Plug for PDS and all the other theorem provers out there, but something very much to consider if you have certain structures to your proof. Some theorem provers may be more ethical, especially if they're information. Something to consider. With that, if there are no more questions and nothing online, let us thank our speaker again for an excellent talk. So our next talk is going to be presented by Arthur Amorum, enforcing Mavlink safety and security properties via defined multi-party session. Arthur, please go ahead.
today we're talking about how to use effects in order to enforce safety constraints, provide some safe. So as a bit of motivation, UAVs have been increasingly deployed in critical domains, such as military operations. And the most recent example of this is how Ukraine is drones take care of their operative bombing. So as they become more and more valuable assets, because they can movement and can automate critical tasks, they also become more and more interesting for attackers to try to sabotage. So typically, an operator communicates with the UAV from the ground location using the protocols, and NavLink is the most widely deployed UAV protocols. However, over the past few years, there's been a number of papers that focus on the limitations of security and safety of NavLink units. One of these papers, which was referenced in the class, is called RV Fuzzer. It shows that there are 87 combinations of parameter values that are allowed by protocol rules, but still cause undesired drone behavior. And these kinds of bugs can be exploited in stealthy attacks. So stealthy attacks assume that the adversary has compromised about specification and is able to send malicious messages that conform to the protocol, and yet still cause undesired behavior. And stealthy attacks are particularly hard to detect because they usually, since they conform to the protocol, runtime monitoring approaches typically focus on anomalies. And the paper was actually able to show that a strong enough event is actually really not on its own, while only using thousands. So the thing that makes stealthy attacks extra problematic is they really exploit this red area of valid command, even protocol rules that unsafe behavior. And first of all, I want to emphasize that runtime monitoring is kind of overloaded. There's runtime monitoring for communication, find messaging extent, and runtime monitoring in the sense of RPVP or even the like protocols and runtime assurance that tries to find requirements and invalidate the requirements. So although something like the simplest architecture can count some self-effect in the backend, because self-effect exploits known applications, actually runtime monitoring approaches are extremely bad at finding, recognizing, and stopping information. So, and to make matters even worse, the paper RB Fuzzer reported 57 bugs and only 7 compensations. So because over 90% of these combinations are valid for malicious attacks and threat entities. So what do you do if you are a drone where it's shipping critical mentions and you know about these attacks and you want to prevent them without having to wait for a patch because it's terrible? So the main contribution to this paper then is a runtime verification approach called data. And runtime verification is different from runtime monitoring because runtime monitoring focuses on anomaly detection, and runtime verification compares communications to a specification. So an engineer can use data in order to write a specification of the protocol and add safety constraints to messages being sent. In the case of, for example, a pitch parameter exploit, where the paper has shown that there are 4 pitch parameters that can be used for mapping, and if 3 of them are set to high values, then the drone can become oversensitive and crash with throwing up just the wind. So datum can you can write constraints to datum that says something like, hey, before you accept the command that may be malicious or what is informed to the protocol, ensure that the other parameters have safe value. So hopefully I've convinced you that datum is important. Datum can be used to enhance safety in stuff because, and we talked a bit about how datum works. So datum is encoded in F-star, and the reason we use F-star to improve it is because it has a native user refinement to Lightspeed. And the 1, 2, 3 for data first to be able to define a protocol. And we go to set the messages such as the parameter updates for pitstone nodes. And we add refinements to the messages that capture safety properties. And lastly, we use data perspectives as runtime. So the first step to NavLink was kind of straightforward because NavLink already had a specification with an XML. So instead of having to write it from scratch and start to write a script that takes a NavLink message in XML format and gets an F-star type that is equivalent to the message, So we were able to really reason about the protocol and stuff. The second step is a little less trivial. There, datum core logic is global, refined, multiple section types, or GRUB, or we call it. So section types is a type theory that allows you to describe communication. And refined for section types is some version of that you can well express. So the two things you can do with GRUB are you can have refinement delivered messages, so you can get very to a message, it's for X. So with a refinement that X must be created in section. You can also have things like double case, where they can send you extra messages. But the message is actually sent depending on which refinement gets started. The third one is I just have the person where you can specify the condition and the value. And because of the pair function, you can multiply it only basically 5 times. So now that I kind of talked a bit about theory, how the data and don't work in practice. So that's just an example of this update parameter for the 26 of Taylor's N. So when we see this command, we really like to get extent. Is this a valid command that would not cause that behavior or might make it be accepted? So we want to be able to check that the 6 parameter values the other 3 have reasonable values to still have to be checked. So data actually keeps track of the idea of this scaling system and all the system variables. So you are able to reference them in your specification. So in order to write a safety property about that prevents self effect, you would go to the part of an album specification that talks about all the documentation making the message, which is a parameter of the fixing of the payload n. And you can add a refinement as part of step 2 and say this n value has to satisfy this constraint that compares it to the current values of the other 2 fixed parameters and make sure that it is safe. So even if n is a high value, if the other 3 parameters are set to non-positive values, data allows them to be properly reduced. However, if it's ever a situation that between 3 parameters that whether the parameter update is can be high value that violates our performance, data will present them as being interpreted by the software and present a possible deviolation traffic. So in order to figure out how data and when the data in our system affects the overhead of the latency and memory, we truly very complicated simulations using arbitrary and big work because we use volume for the software and the implement network. And for latency, we not get precise. It looks worse than it is because something is testing so fast, about 30 microseconds. So the 30 microsecond overhead seems to have made it, but from an actual deployment. So in an actual deployment, where a message takes from 2 to 3 milliseconds to 30 microseconds, jack wouldn't cause much of an issue. However, for memory overhead, our approach currently needs OPNO runtime in order to do checks, and that is garbage collected. So we have plans to improving the memory overhead as we are memory constrained, resource constrained systems. And to conclude my talk, today I talk about data, a runtime verification approach that allows you to add safety constraints to unsafe communication systems and check those are okay.
Thank you for the excellent talk. Do we have questions in the room?
So one thing you show on the slide just before this one is a diagram where you're talking about Datum being used with embedded Linux. In this kind of environment where you're trying to do super highly secure communications, is using this kind of a system in combination with the microkernel-based architecture something in your plans or something you've thought about?
Yes, I actually just presented a paper at ICUL last month that one of Datum's key, like one of the assumptions is that Datum itself is not compromised. But as our keynote said today, it's kind of hard to run a runtime checker and the system itself under the same like Linux. If you've got something like Hackham's attack model that an adversary has root level access to the Linux kernel, then you can officially bypass data and it's still able to cause stealthy attacks. So I actually did a study, a different paper that talked about how do we combine some of the, like a Hackam style architecture of separating data and the file control software in top of SEL4 to prevent something like that. So yeah, I'll point you to the paper after this.
Gotcha. Thank you. Great talk.
Further questions?
So thanks for your talk. I was curious, you talked about intercepting the commands. Is it just like what happens when you intercept the commands? You just get rid of them completely?
So right now, they don't send a signal back to the operator, but our idea is to have something instead of simple architecture, or have a reserve node that can trigger and then take over and cause some fail-safe. The problem with that is fail-safes are very command specific. So at some point, you can return to base, and some you can stop at the air, but it's very specific. And also, you cannot necessarily alert the operator to act because that might be the disjunctive for the attacker. So we could leave that option up to the engineer that's using data, but you essentially get a signal back that says the command is done.
Okay, thank you. Okay.
Excellent work. I just have one question, which is the use case you have shown is speech and high. Are there other use cases? Because speech and high probably is not the worst kind of, for example. Yeah, I could be wrong. Yeah. If you try out something that seriously like the trajectory is being manipulated or something else. Yeah. So another one of the papers, like chemotherapy further, talks about policy guided funding, and it shows that there's nothing that keeps you from sending a deploy parachute command at any point. So although Mavelin says that you should not be finding and deploying the parachute, there's all these preconditions listed. They're not enforced. That command can be sent at any point and can be deployed. So if you're an attacker actually can wait until the drone's driving, when on deploy parachute, you can make the drone crash. And that is not prevented by Mavelin because that was enforced for the operation. So data can add a requirement to deploy parachute command that says, in order to deploy, motors have to be on, barometer has to be decreasing, and you have to be in, so we can control these two conditions at the time of it. So that before you're able to deploy a parachute, data check for them, which is not previously by that matter. So anything that has a policy or a sequence of command that requires something to be safe can also be taken by the time.
Further questions in the room? Going on? I will ask a quick question as we're getting ready to transition speakers. Have you thought about logging these particular stealthy attacks? Can you take any records of how many of them you got?
So actually, like the one of the migration field work is that there's a lot of plugging, such as other plugging papers that by getting into some protocol and see this different combinations violate a policy or a contact behavior. And so we have just kind of made a way to, if it's not fixed yet, one fix is, but most of the logging and defining methods, like most of the stuff in different.
Thank you. Let us thank our speaker again for an excellent talk. So we're getting ready for our final speaker of this particular session. It's Nafis Sadman. Will be talking to us about visualizing temporal interval hierarchy. Nafis?
Thank you. Hi, everyone. I'm Nafis, and one of my co-authors, we are from Queen's University in Canada. And today I'm going to kind of discuss our tool paper, and hopefully at the end of the talk, probably you'll be interested to check it out. So this tool paper, we are trying to visualize temporal interval hierarchies. And before that, we kind of have to briefly touch upon a tool or language called Enfer. And one of the co-inventors of Enfer is Professor Kaufman, who is here with us. So at any point, if you're interested to learn more about Enfer or how you can use it on the data, you're welcome to come have a chat with us. So just a primer of why we need Enfer at all is because logs are almost everywhere, and throughout the presentations we have seen, directly logs are like blood vessels in any CPS. So what Enfer does is it helps to process the logs into more human consumable abstractions. To understand a bit more on the context, let's take an example of a very simple log file. We have a log file IRQ, which is an interrupt call, and IRQ return is the interrupt return call, and we have a scheduled task. So what Enfer does is it mines rules, and the rules can be like the machine written, or you can specify the rules for yourself. So what it does, given a particular rule, say IRQ before IRQ return, it will look at the log files and it'll try to create more interpretable tags or intervals for this. So we call this abstraction intervals. So it creates this interval called interrupt that happens from the time span 1 to 10. And also finds this another particular pattern where the scheduled task happens during the interrupt, which is already been mined or patterned by Enfer. So it produces this another interval called schedule, which happens from 1 to 10 as well, with a particular map. So the params here are the data associated with it. So the interval, like the generative interval from Enfer, if you take a hypothetical timeline, it's a block in the hypothetical timeline. It has a name to it. It has a start time and end time, and some data associated given how you're mapping the data from the log files. One kind of evident problem with this is when, say, you are trying to visualize the log interrupt generated from Enfer, and if you try to, like, there could be arbitrary number of generated intervals from the tool. So what happens is that when you create a tool to kind of visualize each intervals, it can stack up a lot. And also it gives us an overlapping problem as, okay, well, like as you saw, like task during interrupt, it's like an overlap. So they have an overlap of two intervals going on together. So how do we visualize this overlapped intervals? We propose to kind of put Ninja, the time interval, into L length of like buckets. We call this bucketing, interval bucketing. Is we divide the interval into L length segments. And if an interval, any interval overlaps the particular segment, we kind of associated that interval to fall in that segment. Additionally, because we don't solve that overlapping problem of get the stack up to a lot of interval in a visualization tool, we want to take advantage of the color shading that we can use in a tool. So we start off with a very light color, and it goes darker depending on how many interval or the particular interval occurred within that particular segment. So this is the case study we did with the heat pump data log, then mine the intervals from the Enfer, and then being fed to our tool. So this is that you can see the colors here gets this color gets darker here, so particularly for this time segment. So these are the interval names, and we have this timeline is the like timestamps. And it gets darker when there is a lot of this particular two intervals are happening in this particular segment. And also, like, for example, in here as well. So what's interesting is that with this kind of visualization, we can also mine some patterns for the particular case study. So we, for particularly for this one, we see two kind of patterns. They're happening. There's some kind of relationship of each of these intervals with each other, so there's a successive like occurrences, but there are also like concurrent intervals happening as well at the same time segment. So this kind of bucketing allows pattern mining, but also solves the problem of overlapping. So another unique problem with the interval that are generated from Enfer is hierarchies. So let's go, if we take this example again of the log files, and from the previous iteration, we saw that it creates this interrupt, happening from 1 to 10 and schedule 1 to 10, given the rules that are defined by the specification. So what happens is that it also finds another instances of interrupt and schedule because it can see that, okay, we have similar data for IRQ N7 and similar for IRQ at N7 here. And the task here happens in timestamp 5 is shared by both of these instances. So the problem that kind of gets created here is, okay, how do we figure out, okay, which, given any generated interval, how do you figure out which particular trace in the log file were responsible to create that particular interval? For that, we kind of propose kind of recursive, or more or less a recursive problem. So what we did do is, for example, we want to figure out, okay, who were the responsible kind of logs, we call them parents for this particular child, which is scheduled, given a timestamp of hypothetical timestamp of 4 to 12. So this is this comes from the schedule rule over here. And if we trace back to this, it kind of says, okay, so the rule says that schedule is created when task is happening during interrupt. And so for that to be valid, both the task and both the interrupt has to occur within that particular time span. Now, what we see is that, interestingly, we could end there, but it doesn't. But interrupt itself is another interval that is mined or generated by infer. For that, we have to go back to finding, okay, so we're going to create this graph as well on the side. So we found, okay, task, in the log file, we have a task 5.5, and we have on the interrupt, we have 4.12. So as I said, interrupt is another interval generated by infer, and we need to find out, okay, now who created interrupt? So we go back to the log file again to see, okay, is there a particular set of logs that were responsible to create interrupt? And there is. So we find from log file, okay, particularly this IRQ here and IRQ return here are responsible to create this interrupt which spans 4 to 12. This goes, so we cannot validate backwards. Okay, does it validate interrupt? Yes, it does. Does it validate schedule? It does. And finally, does all this together validate schedule, which for all the logs have to be within that time span. So we have this tool which runs on your local machine. It's not on any server, which you can use pretty neat, pretty easy to use it. There is you can hover over the particular interval to learn more about the data, the log files that are responsible for that creating that particular segment. You can learn more about the information on this particular pen, and you can also learn about the rules that created this particular interval. As you can see, we also show that if you were in any point of time we're going to visualize log files directly without intervals, it would create this almost very difficult to interpret kind of a visualization. So yeah, so pretty much to kind of summarize the importance, as Professor has stated in the keynote, that visualization is also a key or kind of an important part in, I guess, formal methods to understand and not to understand, also mine interesting patterns from log files. So yeah, so pretty much, so our next steps for this particular tool is to kind of seamlessly merge this to the language infer. So when you input a log file, it goes through the interval generation to pattern mining from the tool. Then we want to have a display. So it must also have a way to display the hierarchy of, okay, who are the parents or who are the child at particular interval. We want to apply the tool to more case studies with our industrial partners and make it more interactive. What's also interesting that we could dive into, as Professor said, is how probably machine learning could come in hand to hand with this. So we'll try to dig into how vision language models can help us in mining patterns from the tool. And also, we want to make it more scalable. So there could be setting the kind of the obvious thing. Okay, we use the color shading for identifying the density of the intervals. So last night I asked ChatGPT, okay, how many shades of color can a green have? So it says there could be about 5 million possible shades, but we cannot visually kind of differentiate dark green versus a darker green, I guess. So we need to kind of find out another kind of more quantitative way or more like a reasonable way to do this. And basically, yeah, so I hope that this tool, you can check it out when on your data set, and hopefully this will come to like, this will help you understand or mine data patterns from data analysis. So that's it from the presentation, and I'm happy to take any questions. And if you're more curious to learn about Infer and a tool, these are all on GitHub. If you want to check it out, how to implement, I can probably have a chat with you.
Thank you for an excellent talk. Are there questions in the room? Everyone's lunch. Good. Well, I'll start off with a question. Very interesting talk. A lovely detailing of the tool. You mentioned scalability in terms of visualization. You also showed this little tree where you were showing where these traits come from, where are these things being spawned from. Let's talk a little bit about scalability of that particular approach. Do you have means of being able to more compactly represent the series of events which spawn perhaps a particular event or a particular trace in your log file? Because I can imagine that could be very
Yeah, that will kind of expand into like a very condensed, I guess. More like we'll have more branches out for a more complex interval.
Mhm.
But I think what it also allows is you can kind of what you call pruning the tree. You could prune the tree out and focus on one particular interval and kind of iteratively, okay, we have this small tree and we can kind of go backwards to seeing where the I started. So that could be one way of simplifying, I guess, the tree visualization thing for yeah.
Any other questions, comments, concerns? Going once, going twice. Let us thank again our speaker
Thanks.
for an excellent. I believe we are now free or no, it's not
Don't-
done.
Don't offer them lunch yet. We have a short break, half an hour break, and we're coming back for 2 more talks. And then you will all be free to have lunch.
Thank you for reminding me. Enjoy break instead of.
All right. Thank you, everyone, for making your way to your seats for the very last session. We're going to kick off with our first talk, a streamlined formal approach to requirements-based testing by Andreas Kappitz. Take it away.
Thank you, Lauren, for the introduction, and thank you all for staying for the last session of this conference. Today, I'll be presenting a work that we've done at NASA Ames that kind of binds to tools that are under development, to open source tools to enable requirements-based testing from formal specifications. The context that the paper is essentially capturing is that of software verification for safety critical systems, where the certification process for critical applications requires the existence and the proof of coverage with respect to the system that is proposed. And in in the majority of the standards that are have been developed for this particular kind of systems, it is an important necessity to show that their behavior is fully covered and can be exposed by the tests that are generated for them. A particular term that you commonly visit in these standards is that of the characterization of the tests as being requirements-based. And that is because it's important for the tests to be traceable back to the requirements that were written for the system that we wanted to develop. And the main objective here is to analyze the system under test according to the requirements and make sure that the test suites that we develop can be representative of the behavior that was expressed in the requirements at a high level. Towards that end, of course, since the this traceability aspect is important, a lot of automated techniques have been introduced to kind of provide you derive in an automated manner test suites that allow you to create requirement-based tests as a result. And a particular subcategory employs formal approaches to achieving this fact by operating over a formally specified version of the requirements and that are expressed using some sort of intricate mathematical logic. And that makes them also especially important because we can employ the artifacts in an automated manner and use them in an automated fashion to generate tests through formal techniques like model checking. Now, the main problem with incorporating formal approaches in requirements-based testing is the fact that it's very difficult to write formal specifications in the first place. And a lot of times it's very difficult to convince developers to even allocate time to understand formal logic and try to express the requirement of need in some sort of formal specification. So with this work, we're trying to make things a little bit better in this area by introducing a streamlined requirements-based testing framework that starts from an interface where you can write formal specifications by using a restricted English. And to do so, we have in the paper, we essentially extended the a pre-existing formal definition for what consists of a requirements coverage criterion called FLIP to be able to derive requirements-based tests from LDL specifications and also be able to export the artifacts of this process into formats that are digestible by external analysis tools with their own requirements-based testing workflows. The first part of this contribution was an extension in the formal requirements elicitation tool that is developed on NASA Ames. The second part of the contribution is an application essentially of the rules and the extensions that we proposed with this work by enabling requirements-based testing for Simulink models using another tool that is developed at NASA Ames called Symposium, which is a Simulink plugin that allows you to perform compositional verification for Simulink models. And finally, we assessed the effectiveness of our proposed framework by looking into two separate real-world case studies from Lockheed Martin and an internal project at NASA Ames called Proof. So why did we choose FRED? FRED provides you with an interface where the core feature is the ability to express requirements using what we refer to as restricted English sentences. And you can see an example on the right part of the slide here. These sentences, while they're very close to a normal English sentence, can be translated into unambiguous formulas in mathematical logic and specifically linear temporal logic in an automated way. Satellite features in FRED allow users to further understand what they write in terms of these restricted English sentences. And the primary features that allow you to do that is things like diagrammatic explanation of the semantics, the simulator, where you can interactively assess whether your requirement covers the behavior that you intended to, as well as things to formal analysis techniques that allow you to identify inconsistencies between the requirements that you've written. And of course, the tool is open source, and as such, you can have access to it even. And similarly, why did we choose focusing? Focusing allows us to compositionally verify Simulink models using formal techniques such as model checking in the backend. And the specifications that are written in focusing are natively expressed in Simulink in the form of assumed guarantee contracts. The main feature of the focusing is the fact that its ability to translate these Simulink models and specifications into Lustre. And as such, employ state-of-the-art model checkers towards performing formal verification. The focusing framework has also an existing connection with FRED, where FRED's requirements can be imported into focusing to perform formal verification. And since this work was introduced, also requirements-based testing. And finally, of course, focusing is also open source, so it's also accessible to all of you today. So generating requirements-based tests from Fretish. Fretish is the language, is the name of the language that we use in Fret. The objective is, of course, to derive a test suite that demonstrates coverage of the Fretish requirements. And essentially, the idea was to leverage prior work done in requirements coverage metrics for LDL specifications. The area doesn't have a lot of work as a background, but two main approaches were defining a formal criterion for requirements coverage. The first one being unique first cause, and the second one being the so-called flip coverage. Early enough, when we were exploring our options to assessing how to address requirements-based testing for FRED, we identified a couple of weaknesses with the prior approaches, with UFC, unique first cause, having a lack of a formal definition of test adequacy, which in practical terms means that you could have tests that satisfy the proposed UFC criteria while not actually demonstrating the unique effect of anatomic composition in that formula. And on the other hand, the flip coverage metric was limited, provided such a formal criterion, but was at the time limited to future time linear temporal logic. So we chose flip mainly due to the fact that it is backed by a formal definition of what consists an adequate test criterion, and extended that to support the actual fragments that of linear temporal logic that FRED specifications can be translated into. So this you can see the exact fragments in this slide. Essentially, we split the fragments of LTL into two. One that can contain only future time linear temporal logic operators, and one where only past time operators are being used. And as an additional part for this work, we extended flip to also cover bounded versions of the relevant temporal operators, as you can see from the two corresponding syntaxes. Despite the fact that we are limited to these two fragments for the context of FRED, it is important to note that the overall extensions that we propose and the flip coverage as a whole can be used to to assess requirements coverage for LDL specifications that contain arbitrary formulas in future time or past time LDL. So with that being said, I need to, of course, introduce a little bit into the flip coverage metric. It was proposed by Fisher et al. In 2009 and provided a formal definition regarding the unique effect of an atomic proposition occurring in pure future time LDL. And it also provided some incomplete rule transformations for future time LDL formulas that help us identify this unique effect of its atomic proposition. So in this problem, we assume that that we have a formula, a future time LDL formula phi and its atomic propositions. And the main concept that was early introduced in the seminal paper was that of the so-called alpha variant paths. So considering a path that models a particular formula phi, we define alpha variant paths as ones where essentially the evaluation of the states differs only in the evaluations of the particular atomic proposition alpha. The seminal paper makes a certain limitation, which is worth it to note here, and that is the fact that in order to circumvent cases where the same atomic proposition may appear multiple times in the formula, we assume that the formula, the proposed rules are applied to a linearized version of the original formula phi, where its occurrence of atomic proposition alpha is handled independently. This may introduce cases where parts of the formula cannot be covered due to the interdependencies between the multiple occurrences of alpha. But it's also noteworthy to say that since we are also considering this linearization step, this kind of behavior was not identified in the real world requirements that we have used in this case study. So the seminal paper defines a total order relation over paths that essentially captures the fact that if you have a path phi and an alpha variant path phi prime, then the relation essentially says that phi can be less than or equal to phi prime if the occurrence if alpha occurs more often in pi prime, is true more often in pi prime than in pi. And given this total order relation, then we can characterize a formula phi as being covariant if alpha variant paths where alpha is true more often preserve the satisfaction of the original formula phi, or contravariant if alpha variant paths where alpha occurs is true less often preserve the same satisfaction. And of course, the formula phi is defined to be monotonic if it's either contravariant or covariant. So the main definition is at the top of this slide. We say that a path phi is an adequate test case for atomic proposition alpha in formula phi if the path models the formula phi, of course, and an alpha variant path of it exists such that this alpha variant path does not model phi. So in essence, the diversion between the evaluations of atomic proposition alpha in the two paths result in a violation of the original requirement. And as such, we define a set of rule transformations where if phi satisfies those transformations, then is part of the flip set of paths where we can identify alpha variant paths that can violate the original requirement. If as such show the unique effect of alpha in the process. So the seminal paper introduced the rule transformations for future time LTL that you see on this slide. And essentially, each one of them essentially expands on the original formula. So part of each rule requires, of course, the satisfaction of the original formula. But in addition to that, additional constraints are introduced that ensure how the atomic proposition alpha can uniquely affect the satisfaction. And as an example, a very simple example here, I have this example on the right, where we have the original formula phi being globally A or B. And if we wanted to derive a formula that covers A, we get globally A or B, and eventually A and not B, which would admit paths where eventually the satisfaction of A is uniquely shown to be affecting the requirement, the original requirement. So with the already established rule set, we proceeded with extending the clip coverage metric to make it compatible with the entirety of thread and the LTL formulas that we can derive from thread specifications. And these are the rules that we resulted in here for pastime LTL, as well as the bounded version of LTL operators. And for the majority of them, the main idea remains the same. So we need, of course, the original requirement to be satisfied, but we have additional constraints that limit the context, the frame, into specifically trying to show alphas in effect. In the slides, I've outlined the case for the Z operator here because it kind of diverges from the rest. And that is because if we consider the definition of test adequacy in CLIP, we would not be able to derive tests from paths of length 1 in the case of the Z operator, because every path of length 1 satisfies the Z operator in the initial state. So we circumvent this intricacy by enforcing the consideration of paths longer than length 1 by using the yesterday operator as the rule in this case. As another example, you can consider maybe the case for SINs here, where phi alpha designates that alpha occurs in alpha and phi prime does not contain any entarities of alpha. And you can see how the corresponding rule reserves, of course, the original requirement, but also requires that at some point we have encountered a state where phi of alpha is true because of alpha. And this also, of course, gives the rest of the CLIP rules to actually identify what that means and eventually come to a set of paths, where we can identify alpha variant paths that violate the original specification. As part of this work, we extended the CLIP coverage criterion, and as such, we also needed to prove the soundness and completeness of our proposed rules. And toward that end, we used the theorems expressed in the seminal paper to do the same for the extensions that we propose. The main two theorems are theorem 2 and 3, where we are essentially covering the soundness of our proposed rules and the completeness of them, which essentially captures the fact that any path that satisfies the formula and for which path an alpha variant exists that violates the same formula, then we have a path that is admitted by the corresponding proposed CLIP. Both of those theorems partially depend, the proofs of both theorems partially depend on theorem 1, which defines extremal variants in our case, where if for the covariant case, if phi is covariant in alpha and a path at which it models the rule transformation that we proposed, then alpha variant path where alpha is false throughout the entire trace does not model phi. So with the proposed rules, of course, the objective is to generate tests that essentially cover the entirety of the specification following the clip, coverage metric. And in order to do so, we negate the derived formula and we perform a model checking action for each such formula on this negated trap formula. Depending on the results of this model checking task, we can have different cases. The most popular case is that we can successfully derive a test that covers alpha in phi, and in those cases, the negated trap formula is invalid, and we retrieve a counter example that shows how that can show how alpha uniquely contributes to the satisfaction of the formula. More interestingly, if the negated formula is valid according to the model checker, then additional investigation is needed because it is not clear whether at that point whether the model has any interdependencies on alpha, such as cases like strongly coupled atoms that we encounter in MCDC problems. And as such, you need to further identify whether these interdependencies are desired in the model that you are considering. Finally, if phi is invalid and the negated formula is also invalid, we have a very intricate case where a design error may actually exist in the model because we intuitively we retrieve a counterexample that shows how phi can actually be satisfied because of alpha. And since our original property was essentially a negative property with respect to the model, there's something that must be going on wrong with respect to the implementation if alpha can actually be used to derive an execution that satisfies this negative property. So for the purposes of this work, again, we used the existing connection between Fred and Cocosynth to enable requirements-based testing from specifications written in restricted English. And the main part of this connection has already been there prior to this work, and it allows you to derive the formulas, the pastime LTL formulas of the corresponding Federal specifications and automatically translate them into equivalent signaling blocks that can be further analyzed by Cocosynth and produce tests in our case. So this is how the resulting framework looks like after our extensions. The boxes with the solid color background are the parts of the two tools where we had to perform additional extensions to achieve what we have today. On the Fred side of things, the most important part to outline is the fact that we can actually derive test cases without the existence of a model. So we can just use the requirements themselves to derive tests that achieve clip coverage. And on the right-hand side, for the case of Cocosynth, of course, we had to extend the existing connection between the two tools, the interfacing between the two tools, so that we can account for the purposes of requirements-based testing, and also added ways to translate the provided counterexamples from the underlying model checking tools to represent them as executable test vectors at the Simulink level. And with that, I have a couple of video demos to show you how these two extensions look like. Starting with Fred, this is the main window that users will interface with. And that is the requirements editor where we can write requirements. Considering that we have a set of such requirements, we can switch over to being able to export these trap formulas that we have introduced using Fred's interface. And in this case, for this example, what I used was to export the past time LTL clip obligations in the format that Cocosim uses. It's called the CocoSpec and it follows the assumed guarantee format. In addition to that, we can also export the same obligations in future time or past time using the SMV format. Then the second part of this video shows you the test case generation interface in Fred, which does not consider a model at this level. We are just using the requirements themselves and try to generate tests that cover, that achieve clip coverage. And as an addendum to that, we can actually interact and view the tests within the interactive simulator, as well as, of course, export the tests into a simple JSON file for additional analysis by external tools. The second video shows you how things look like on the Cocosim side, and the thumbnail is essentially the result of importing Fred specifications into Cocosim. And at the top right, you can see the contract block, which contains these obligations inside. And given the specified set of clip trap formulas, you can then use the Cocosim the Cocosim extensions that we performed in the interface to generate the requirements based tests that try to achieve full clip coverage. See. Yeah. So, for example, it's simply working, so I'll just. So, given that we've essentially selected the action to perform the requirements-based test case generation, we result in a set of test cases in the form of Simulink test vectors that have been attached at the right hierarchical level of the Simulink model that we wanted to derive tests from. The last part of the presentation looks into the evaluations, into the evaluation of our work based on two real-world case studies. The first one being a set of cyber-physical challenges from Lockheed Martin, and the second one being an internal project at NASA Ames towards the development of multi-agent rover swarms. For the majority of the case studies that we looked at, we were able to achieve full clip coverage. There are a couple of cases from the Lockheed Martin case study where non-linearities prevent us from actually generating counterexamples, and those are the not applicable cases here. And other than that, there are two intricate cases that we can kind of focus on with respect to the coverage not being 100%. And those were actually related to two more involved cases than just being unable to cover the particular atomic proposition. With the first one being a case where we can identify vacuity in the original specification, since the highlighted part of the practice requirement could not be shown to be covered by the resulting trap formulas. And that was due to the fact that in the Simulink implementation of the model that corresponds to this requirement, the autopilot component, the roll fault mode can never actually be activated. The second intricate case was actually an inconsistency between the specified requirement in British and what the actual implementation was doing. And you can see the implementation in the bottom here and the requirement at the top. And more specifically, the fact that the obligations for the two atomic propositions here could not yield tests because it was not possible to show the unique effect with respect to the cases where we are not exercising the send transition state in the output of the underlying model. And as you can see here, the inconsistency relies in the fact that in the implementation is much weaker than the actual requirement, since the requirement specifies that both signals need to be false at the same time in order to perform the transition, whereas the actual implementation allows more behavior as part of the signal for implementation. And with that, I'd like to conclude and direct you to the links that you can use with the QR codes for further information. And thank you for your time.
Thank you so much. Okay, we have time probably for any questions. Yes, Barry?
Thank you. That was really interesting. So in the flip formula, you're sort of characterizing places that are like the keeping constant until one of the variables, like one of for like where the assignment of one variable stays constant between places. Are you able to do this for like multiple variables? Can you define like try differently if like a V pipeline for the two variables?
So we are not currently addressing this, and that is actually something that we would need to do in order towards addressing cases where strongly coupled atoms may exist in the specification. But for this, the way that these rules are introduced, target a specific variable at any time, not a collection of variables.
Thank you.
All right, let's thank our speaker one more time.
And our next speakers.
All right. Last but certainly not least, Alec Rosentrader is going to be presenting on language partitioning for mission time linear temporal logic.
Thank you. So this is joint work with my co-first authors, Zoe Wang, and as well doctors Catherine Fassian and Christian Rosier at Iowa State University. So let's jump right in. Safety critical systems oftentimes start their lives as long lists of English specifications that are drafted by system designers and stakeholders from a variety of domains. So they come together and they write long lists of English specifications. In this example, we have an example requirement that says the spacecraft shall deploy its solar array within 10 minutes, or the spacecraft will remain in low power mode, which is a fine English specification, but it's not formal. And the elicitation problem that Andreas talked about with what Brett addresses is a well-studied problem, but we'll just run through this example quickly. So we want to start identifying some actions that this requirement addresses. So we can say deploying the solar array is an action. So we'll want that to be a Boolean variable in our formal requirement. As well, we have some time bounds on this. So we say within 10 minutes, we need an operator to capture the time bounded nature of that. So we can say in the future, between 0 and 10 minutes, we need to deploy the solar array. And then as well, we have this or, so we need a disjunction. And then we have another action, remain in low power mode. So we can say low power mode is another Boolean variable. And this has a remaining operator. And so we can say that is a global operator that reasons over the same amount of time. We have this now formal specification, which handily happens to be captured in mission time linear temporal logic, which is a finite variant of LTL that places closed interval integer bounds on all the temporal operators. So we have the 4 main operators that temporal logicians are familiar with: globally, future, until, and release. Notably, MLTL discards the next operator because it's equivalent to in the future 1, 1. So that's just a syntactic thing to simplify language. So if we return to our formal specification, we can start looking at how do you meet the specification. And so we can say there are perhaps some different ways to do that. And one particular way you could do that is you could just deploy your solar panel at some point. We don't really say when, but that's what you will want to do. Or another potential behavior is you want to stay in low power mode. This is acceptable. This is defined in the requirement as acceptable behavior. And so we would want to be able to say something about that as well. And because of the way that this was formalized, there's actually a third option where you can do both. And this is something, it's an artifact of the formalization that is maybe not what the system designers intended. They are stakeholders from various domains. They are not super necessarily familiar with formal logics. And then if we dig down on this behavior 1 a little bit more, we want to say, well, when do you deploy that solar array? Do you do it immediately? Do you do it in the middle of this acceptable window? Or do you do it at the end? And it doesn't necessarily seem relevant just looking at the specification, but if you're doing verification, there may be simultaneous components that could interact potentially if you don't investigate all of these. And so we come to the question of, well, how do you describe these behaviors formally? And so if we consider how do you break down an MLTL specification into these behaviors, we can say that behaviors correspond to sets of traces, and the language of a formula, and we can just say is the set of all traces that satisfy that formula. And that is just a set representative. But if we want a subset of this larger set, how do we capture that meaningful subset? And if this is a set of traces, well then that also is described by a formula. And so we can introduce the notion of a co-formula, which has a language that is a subset of the original formula. And so a co-formula is semantic in nature, as opposed to a syntactic subformula. So for example, in the future 0 to 3p is a co-formula of in the future 0 to 10p, but it is not a subformula. So if we have a formula phi with co-formulas psi1, psi2, psi3, for example, we would want to make sure that we would want to describe all of the traces in phi. So we can do that with what we call a language decomposition, where every trace in the language of phi is described by the language of the co-formula. And so we capture all of the traces. We don't enforce a disjointness. We just say that the co-formulas union together to be the language of the original formula. If we want a slightly stronger notion, we can instead investigate a language partition where the co-formulas not only form the union forms the original language, but as well, the languages of the co-formulas are disjoint. And that is a slightly stronger notion. And a language partition is a kind of a language decomposition, but a decomposition is not a partition. And then, of course, we come to the question of how do we do this algorithmically? So we introduce this language partition function to compute language partitions. It takes in a formula and it returns a set of co-formulas. We require well-formed input in negation normal form, where your only negations are in front of variables. This just simplifies computation a little bit, makes it easier to reason about formulas. And then as well, we take in this recursion depth parameter D, which controls how far down the function recurses on the abstract syntax tree of the formula. And that just provides flexibility and a little bit usefulness for implementation and working with the function. So we have to consider not every formula is actually able to be partitioned. Some formulas, like the atomic formulas, true, false, a Boolean variable or a negated Boolean variable, just simply can't be partitioned. So those we have to return just the original formula as well. If the decomposition depth is 0, we include that for a reason. And so we just return the set containing only the original formula. This, in fact, on this case, the function returns both the decomposition and the partition, which is good, which is what we had wanted. If we look a little deeper into the Boolean connectives, we can investigate the AND operator first. And if we're computing the language partition of some formula phi and psi at a depth, we'll want to recurse on the subformulas and compute the language partition of each of the subformulas. So in this case, phi might have language phi1 and phi2, and the language partition of psi might have coformulas psi1, 2, 3. And then when we are returning up the recursion tree, we'll want to compute the conjunction of all possible combinations of the elements of the two sets. In this case, this does provide a decomposition and a partition, which is what we wanted. The OR operator follows pretty similarly. We're computing language partition of a disjunction. There are 3 ways to satisfy a disjunction, where you don't satisfy the left formula, but you do satisfy the right subformula. So we recurse on the right subformula. Or we as well want to investigate the case where the left subformula holds, but the right does not. And then as well, we want to investigate the case where both of them happen. And so we do some recursion here, and then compute the union of those sets. That returns, in this case, a decomposition and a partition, which is what we had hoped for. Temporal operators, however, are a little different. Because this is MLTL, the temporal operators have these intervals, and we need to consider how do you break up the intervals. And because MLTL has integer bounds on the intervals, we can use integer compositions, where you break up an interval or an integer into a series of smaller integers. So for example, 8 will be broken up into the sum 2 plus 4 plus 2. Or if we take this example where we have an interval that runs from 3 to 10 on some composition 2, 4, 2, we can produce 3 intervals that run from 3 to 4, from 5 to 8, and from 9 to 10. Notationally, we handle this just as the angled brackets in the superscript, and this keeps our notation nice and compact and makes it easier to work with. So if we look at the example of the future operator, we can compute the language partition of, in the future, 3 to 10 on this composition 2, 4, 2 at some subformula phi. And we can recurse on these different intervals that we produced with the composition. So we can first recurse when phi happens in the first interval, and then we can recurse on the case where phi does not happen in the first interval, and it first happens in the middle interval. And then as well, we can do that where phi happens first at the end of the interval. And this produces a decomposition. Great. Does it produce a partition? No, it does not. And this is something that we found as we were developing the algorithm. And it does not produce a partition because of counterexamples like this, where you are trying to compute the language partition of a temporal operator. In this case, we have in the future 0 to 5 on the composition 3, 3, P or Q, and then we want to do a decomposition at depth 2 or greater. And so if we compute the first high level language partition, we can get 2 coformulas, and then we get in the future 0 to 2 P or Q, and we can move down the recursion tree again and compute the language partition of this now. And this is going to produce 3 coformulas in the future, P and Q, in the future, not P and Q, and in the future, P and not Q. And as it turns out, all 3 of these are satisfied by the trace PQ, Q, P. Because of this, the temporal window is wide enough to allow all 3 of these to be satisfied by one trace. And so these are not disjoint. and this fails the partitioning condition. Other temporal operators, the until, release, and globally operators were all implemented similarly, where we characterize when something first happens and not earlier. And so we see similar counterexamples for all of them, where the decomposition depth is either too deep or the interval composition is too wide, and we lose the disjointedness and partitioning conditions due to that. So when do we get a partition then? Well, we wrote some proofs, and we were able to prove that for any well-formed MLTL formula at any arbitrary depth on any composition shape, we do always return a language decomposition. So the full language of a formula is always captured in the language of the coformulas. And we were able to define some restricted conditions under which we do return a language partition. In particular, we trade off decomposition depth or composition shape flexibility. So we can guarantee returning a partition for any well-formed MLTL formula at any depth if you take the integer composition of all ones, or you can take any well-formed MLTL formula and return a partition on any composition shape if you limit your recursion depth to 1. And how do we know that these proofs are correct? Well, we formalized it. So we formalized our algorithm in the Isabelle-Hole theorem prover. The executable algorithm was around 200 lines of code, whereas the proofs took around 6,500 lines of code, which is available on the Archive of Formal Proofs, which is a large online repository of Isabelle proofs that's used by the research community. That's available on the entry entitled Mission Time LTL Language Partition. Okay. The formalization was not without its challenges. We had to define a new data type, the MLTL extension data type, which to interface with the existing MLTL formalization. The old one did not have support for the integer compositions that accompany the temporal operators. So we had to define a new data type to store those. And this presented a challenge both in writing the proofs and constructing the proof structures, just because we had to convert back and forth between these data types so much. As well, the release operator presented significant difficulties just because of its semantics. Sometimes the proofs went up to 4 layers deep with 20+ subcases for each layer. So this temporal operator was very annoying to prove. But the formalization did reveal the previously seen counterexample as we were developing the algorithms. There was a lot of value that we found in developing the formalization as we were writing the algorithm. But we have to ask, is this formally verified algorithm useful? Does it have applications? And so to investigate this preliminarily, we did a little bit of a case study on doing some trace generation coverage. So if we return to our previously seen example requirement from the introduction, we have simplified here a little bit. In the future, 0 to 10p or globally 0 to 10q. And the trace generation coverage problem is we want to find a representative set of traces over this formula. And in this case, we just define representative to mean coverage of the coformulas. So a very simple coverage metric for this limited case study. So the formatting is messed up, I apologize. We want to first, to compute the language partition, we need to add an integer composition and then set our recursion depth. And then we can compute the language partition with the code that was exported from our Isabelle formalization directly. And so computing this, we get a set of 7 coformulas. They are very long, but something to note is they are not ordered. And so the ordering, they are indexed and not ordered, but they are very long and messy. So we want to compare our approach against some existing techniques, and the current state of the art for MLTL specifically is just doing random sampling, where you generate a trace randomly of a given length, and then you check to see if it satisfies the formula. Or you can do some trace enumeration, where you sample multiple unique traces from a sat solver, just given a basic one. So how did we do? Random sampling, we queried 500 traces randomly, and they returned 12 traces that satisfied only coformula number 4. So not a very diverse set of test cases just from random sampling. If we move to trace enumeration, we queried 50 traces, which again primarily returned traces that satisfied coformula 4, but also some that satisfied coformula 0 and one that satisfied coformula 5. So a slightly more diverse set of traces. We did get the number of traces that we asked for that satisfy the formula, but still not very diverse. If instead we move to querying one trace from each of our coformulas, we can establish baseline coverage very easily without much difficulty. But then if we want to push it further, what we did was we did trace enumeration on the coformulas. And that was able to produce not only baseline coverage of the coformulas, but as well, it produced a number of traces from coformulas 0, coformula 5, and coformula 4. And the others in this case were primarily timeout limited. The formulas very rapidly got very large that we were feeding into the sat solver, and the technology just wasn't there. So these are our results on the whole. But if we want to look at something a little different, we can compare our results to the total number of satisfying traces from each coformula. So the coformulas have different numbers of satisfying traces, and we can see that our approach not only mimics the shape of the distribution, but maintains coverage over the coformulas. So trace enumeration also somewhat captures the distribution shape, but it does not have that coverage over the coformulas. So overall, we have formally verified language partitioning for MLTL. We have our results available on the archive of formal proofs, and we have demonstrated a small practical application. In the future, we want to look at broadening our disjointedness theorems. So in this example that I showed in the results, the criteria for meeting a partition were not met, but the algorithm did return a language partition. So there are more cases where we do return a partition than we necessarily guarantee with our theorems. So the current conditions we know are sufficient, but not necessary. And as well, we want to explore more applications, such as model checking, test case generation, and other ones as well. So this is all I had for the presentation. Stop here for questions.
Questions?
Thank you very much. And maybe I miss a part, like how do you choose the decomposition? And a related question is, I mean, you showed some examples where you don't have like a partition, but does it exist for some other choice of the decomposition that then it's partitioned, it's properly partitioned?
Yeah, that's accurate. So you can choose interval compositions that don't give you partitions. We defer that to use cases. So some test case generation applications might want to guarantee the disjointedness, and that would be on a case-by-case basis that you have to choose the interval decompositions. In the future, we would like to find an automatic way to do that, but that's future work.
Okay, so for the moment, that the user that explain how we want to keep the 10-step intervals into.
Yes.
Okay, thanks.
Thank you for the excellent talk. So my question is more, I'm not so knowledgeable about MLTL, specific variants of LTL. So it's about the expressivity of LTL and MLTL in particular for more realistic scenarios for satellite, like solar panel deployment, which is very critical operation. So if someone wants to include things like the satellite is still in transfer orbit, right? It's not at reach actually that orbit. Or something like is the panel deployed properly? It has to exactly be at 90 degrees to maximize solar output. Because all the the temporal operators I saw, and I could be wrong. It seems like it's just looking at the traces of a finite state of mind.
Yeah, MLTL is a finite. Yes.
So is it expressive enough to take into account what are there other like control logic extensions which can take into account scenarios like this?
There are a number of extensions for MLTL, but in general, I believe most practitioners have found MLTL to be sufficient for their needs. I'm happy to chat offline about other cases.
More questions? Right.
So I guess I had a question, kind of working in interactive theorem gurus myself, and fighting those dragons and finding those places where you get stuck and that process of going back and finding those edge cases. So how did you know that when you reached that point where you had to like redefine things, what was the choice being made at that time of like how things got redefined? And I'm curious about your thoughts on like why Isabel and those kinds of questions.
Yeah. So the why Isabel was it was a pretty straightforward choice for us. There's an existing formalization of MLTL that we could interface with. And so that made the extension pretty natural to us. We actually started this effort. We had pencil and paper proofs. And as we were starting to look at those, we were like, okay, we've convinced ourselves, but we don't trust ourselves. And so that was what led to the formalization. And also, my co-first author, Zilly, loves Isabel for some reason. So, yeah.
Yeah, awesome. Thank you. Yeah, kind of pick the tool that works.
So it is good that you have the formalization because the devil is in the detail. For example, for the join, do you really mean that is the join everywhere or that is the join everywhere except at the authors formula? So for example, if you have x greater or equal than 10 and x less or equal than 10, and it is the join.
So the value of 10 would only be present in one of the co-formulas at that point. So,
Okay.
yeah. So 10, like if you have greater than 10 and less than equal to 10, 10 goes with the less than equal. So we have it broken up on the intervals. I can show, we go back. Sorry. Back here. The intervals are broken up such that they don't cross count.
Okay. Uh, you can always decompose with zero, but I imagine that zero is not allowed or.
All right, any last questions? If not, let's thank our speaker one more time. I'm gonna hand this mic off to Laura to close us out. Lauren. So we have reached the end of NFM 2025. Yeah, that's like, first of all, but thank you so much for being here. I hope you enjoy the conference. I think it was a very nice program that Aaron and Laura put together. So this is a little summary of the numbers of NFM. So we got 65 papers that have been submitted that were reviewed, and we accepted 24 of these, and so up 37% acceptance rate. So congratulations to the presenters here and others. And we had 71 registered attendees in person and 66 virtual. We had 3 keynote talks and 4 keynote speakers and 8 sessions in total. And we had so many countries represented from Europe, North America, Central America, South America, and so on, even Australia, maybe. Yeah. So thank you for being here. Special mention to the Best Paper Award that this year was awarded to S&P formalization of mixed precision metric multiplication. And also congratulations to our other 3 runners-up. First one is a verification of an anti-unification algorithm in PBS. This paper that has been just presented by Alex, so language partition, information, time, linear temporal logic. And finally, the formal verification of composite field multiplier for information theoretically secure radio communication in spacecraft control. Oh, that was a long title, but yeah, congratulations. As I said, they were all very equal in the in our poll. So congratulations to everyone. Thanks for our to our keynote speakers. I think they did a wonderful job, and all the keynote talks were excellent. And finally, well, thanks to everyone that organized this conference. First of all, thanks to Ifansan, which was the local organization chair that helped us organize NFM here at William and Mary this year. Thanks to Aaron and Laura for putting together the program. Thanks to Mariano and Cesar for organizing the PBSA and also helping with the local organization. And to Tanner for publicity. And thank you all to the author, speaker, session chair, program committee members, attendees, student volunteers, a special thank you to you. And to Azul Lopez and the graphic design team for the badges and the posters, etc. And thank you to Abigail, of course, because she was wonderful. She helped us putting this together, virtualization, YouTube streaming, etc. That was great. And also last minute virtual talk wasn't easy. So thank you, Abigail. Next year, NFM will be organized by the JPL, NASA JPL, and the University of Southern California. It will be held in May 2016, and the organizer will be Giovinai Deshmut, Klaus Haveland, and Alessandro Pinto. So see you next year, hopefully, at NFM 26. And goodbye. Now you can have lunch. Bye.
And thanks to Laura as our general chair. She did an excellent job.